for being here, and we're looking forward to the engaging discussions ahead. So, I would like to invite Professor Dr. Sunil Kumar, Head of the Department, Computer and Communication Engineering, to address the participants and to shed light on the FDP and its objectives.
Thank you, Dr. Soumya. A very good evening to Professor Kuldeep Sangwan, Dean Faculty of Science, Technology and Architecture, Professor Amit Soni, Registrar NUJ, Professor Rohit Bhatnagar, Associate Dean, School of Computer Science and Engineering. A good teacher needs to be a good learner as well, and we know learning cannot happen in isolation. In this context, FDPs are great platform to learn from each other, even crossing the geographical boundaries and domain expertise. It's my honor to welcome you all to 1 week ATAL FDP on AI-enabled collaborative learning in 6G and beyond. The FDP is organized by Department of Computer and Communication Engineering, Manipal University, Jaipur. We are proud to have this FDP is having around 10 experts from across the globe. Out of them, 8 are academic and 2 are industry experts, because talking about an advanced topic like 6G and artificial intelligence role in making it better and efficient, it's paramount that we don't really limit the geographical boundaries. So, and also the expertise, because industry insights are equally important. So we are able to have 2 industry experts with us. They will share their opinion and their views on 6G and beyond. Apart from that, we have 2 experts, one from University of Auckland, New Zealand, and another from Georgia State University, Atlanta, USA. And they will really provide the international perspective, how people are thinking and working on such an advanced topic. So we are fortunate to have a real amalgam of academia, industry, and across the country and across the globe. More than 200 participants across the country have registered for this FDP, which is very pleasing. And I think together we can really take it forward and have a very nice discussions and learning from this FDP. Over the course of 6 days, the FDP will cover a wide range of topics, including AI in autonomous 6G networks, integrated photonics, generative AI, and much more. This session will provide the technical knowledge and foster critical thinking and interdisciplinary collaboration, which is very important nowadays. I hope this FDP will serve a platform for knowledge exchange and inspire new ideas and obviously new partnerships. Once again, I extend my warm welcome to all, and particularly to all participants. Thank the MUJ management for supporting us so well, and the conveners who have done all the hard work, and now it's up to all of us to make best of it. Thank you one and all. Thank you very much.
Thank you so much, sir. Now I would like to request Professor Dr. Rohit Bhatnagar, Associate Dean of School of Computer Science and Engineering, to brief about the school and elaborate on the expected outcomes of the FDP. So please.
Yeah. Thank you, Dr. Soumya and Dr. Sunil. So I welcome each one of you, the participants, the resource persons to this FDP program from ATAL scheme of AICTE. And it's a very, as rightly set, the context is already set by Professor Sunil. And it is a very relevant domain or area on which the FDP is being planned and executed from 20th to 25th of January. So regarding the Department of Computer and Communication Engineering at Manipal University, Jaipur, which is the host of this hosting department of this particular FDP. The Department of CC started functioning in the year 2015, and department has got 28 faculty members currently, and around 1,000 students who are enrolled with the department and department conducts research in almost all the fields of computing domain. And we have good faculty from various top ranked universities, and the spread is across India. So this department is, although new, but it is a focused department, and the faculty members are contributing not only in research but very effective teaching for the students. And the students are also getting a lot of accolades for the university and for themselves. So I wish this department great success in all the endeavors which they undertake. And this AICT Training and Learning Atal Academy, AICT New Delhi FDP on AI-enabled collaborative learning in 6G and beyond is a very relevant topic on which the FDP is being conducted by this CC department. And I congratulate Professor Sunil as HOD and his team for this FDP, planning this FDP, and also the conveners, coordinators for this. My voice is echoing, I think.
It's fine,
Okay.
sir. Please carry on.
Yeah,
Please
yeah.
carry on.
So the coordinators, I congratulate the coordinators also, Dr. Arvind Dhaka and Dr. Lal Pratap Verma for coming out with this FDP program, and for submitting their proposal to the Atal Academy and getting this FDP from them. So, as pointed earlier by Professor Sunil, this FDP is very much relevant in today's world, and AI-enabled collaborative learning is emerging technology which is set to revolutionize the complete domain of learning, teaching, learning, and computing. And the learner's learning experience are enhanced through features like real-time feedback, gamification, and intelligent moderation using AI tools and techniques. So this FDP, I'm sure that with the spread of the resource persons across the globe, from across the globe, will help you in gaining understanding about this domain, and to apply the learning in your day-to-day life after this FDP is concludes. And I'm sure that you'll be learning various new techniques, tools, and apply them. And this area is wide open for research as well. So you'll learn, or you'll understand about a lot of new avenues which are there from the research perspective also. So I wish each one of you very happy learning, and I'm sure that from the resource persons from top IITs, NITs, and foreign universities, you'll be gaining a lot of insights into this particular domain, and wish you again very happy learning, and thank you so much. Thank you. Over to you, Soumya.
Thank you so much, sir, for the best wishes and your words of wisdom. Thank you so very much. Now, I would like to request Professor Dr. Kuldeep Singh Sangwan, Dean, Faculty of Science, Technology and Architecture, to inspire us and the participants with his vision and expertise. So, please.
Thank you, Dr. Soumya. So, as a Dean of Faculty of Science, Technology and Architecture, I welcome you all, the participants in this FDP, Atal FDP. So, generally, I take very less time to speak out. So, First thing is that world is evolving at a very fast pace. All of you agree, and particularly the computing branches, they know it. Whatever we are teaching 3 years back, those things become obsolete very fast. So there is a big challenge for students as well as the faculty. It's a very critical junction. Whatever experiences we gain, so that we have to share with others. The experiences, the perspectives from the different people are different. So when we share them at the junctions like FTP programs, then we elevate each other. It's a learning, it's a knowledge sharing by the supporting one another, and we grow together as a nation. So the type of skills required for the student, that is also changing. Whatever skills required, like computing, if it comes to my mind, coding with the chat GPT and generative AI, what type of newer skills will be required for the students, that also we need to bother about. So when we develop, we learn together, it's better than we are better equipped to take care of the students' need for future growth. So collaboration is another one which is required. And I'm very happy that our CC department is doing this ATAL FDP on a topic which is 6G and beyond. Not as a dean, but as a personal researcher in the manufacturing environment in Industry 4.0 smart manufacturing, I know the importance of communication 5G or 6G. When thousands of industries and with many thousands of sensors, they're working together, we need to transfer the data quickly. We have to acquire the data and transfer, and we have to make a decision to run our automated distributed manufacturing systems. And for that, we required a lot of 6G. So maybe in the medical health and this. So I'm very excited about the topic, and myself will be attending one or two of these programs. I'm sure that not only the faculty members, but our distinguished guest also, for the resource person, they will also be learning from each other and they will connect with each other. These type of activities not only for like our personal growth, but they make our connections much faster in this world. And the insights and connections, I hope you will get during this connection about the FOSTA, the insight topic. So this FOSTA is only not even 1 month old. It's a Faculty of Science, Technology and Architecture. So here we have more than 10,000 students, more than 500 faculty members, and more than 20 departments, exactly 20 departments, and having 23 degree programs, undergraduate degree programs. That is the scope of this. So let me congratulate our Associate Dean Rohit Bhatnagar, Professor Sunil Kumar, and the coordinators and the DRC member, Dr. Somya, for organizing this ATAL FDP in an area which is very interdisciplinary in nature. As I told you, the 6G and beyond, that's required for different type of industries. It's not only academic importance, it has a lot of industrial importance. And I'm very happy to note that there are few members from industry who will be resource persons. So I'm sure they will bring forth an industrial perspective to this. So let's us begin this journey with a lot of energy and optimism and the commitment to take place and progress in the coming times at this late 6 o'clock. I know many people don't have the energy now. So thank you very much, everyone. Thank you very much.
Thank
Over
you
to
so very
you.
much, sir. Thank you so very much, sir. We, as the faculty members, are always inspired by your passion for the teaching and research. But today you spared your time and shared your experience with the participants also. So we are very grateful to you, sir. Thank you so much. So now I would like to request Dr. Arvind Thaka to propose a vote of thanks, and then we will start with the first session.
Good evening, everyone. Dr. Soumya. It is my privilege and honor to vote of thanks.
You just
Okay, for this inaugural session of 1 week online faculty development program on AI-enabled collaborative learning in 6G and beyond. On the behalf of Department of Computer and Communication Engineering, Manipal University, Jaipur, I extend our heartfelt gratitude to all dignitaries, participants, and organizing member for making this event a grand success. I would like to express our sincere appreciation to Dr. Sunil for his warm welcome, and thank you Professor Rohit Bhatnagar for his enlightening overview of the School of Computer Science and Engineering, also Computer and Communication Engineering. And again, thank you Professor Kuldeep Sangwan for his inspiring word about the Faculty of Engineering. A special thanks to AICTE of their support in sponsoring this FDP. This encouragement and commitment to empowering faculty members are truly commendable. To our esteemed international or national speaker who will guiding us throughout the session, we are deeply grateful for your participation. I would also like to extend my gratitude to the organizing team for their hard work and dedication. This event would not be possible without your meticulous planning and seamless coordination. To all participants, thank you for joining us. Your enthusiasm and curiosity are what make it initiative like this meaningful. I encourage you to actively engage in the sessions and make the most of the unique learning opportunity. Lastly, I thank the leadership of management of Manipal University Jaipur for their unwavering support and encouragement in hosting program of this scale and impact. Let us continue to collaborate, innovative and inspiring as we embark on this journey of exploring AI-enabled collaborative learning in 6G and beyond. Thank you all, and I wish you a fruitful and successful FDP ahead. Thank you so much.
Thank you so much, sir. Now let's start with the technical sessions. And today, at the very first day and the very first session, we have Mr. Sanjay Kumar, the senior telecom and cloud professional with us for this session as a speaker. Sir, can you please turn on your camera?
Yeah, I've just done that. Yeah. Can you hear me? Hello? Hello? Are
Good
you able to
evening,
hear me?
sir.
Yeah, can you hear me?
You are not audible. Can you please turn on your mic also? Good
No,
evening, sir.
No,
it's
he's very
turned on.
much audible, Dr. Soumya. I can hear him.
Yeah, he's audible, sir.
Yes, yes.
Maybe you have muted your laptop. That may be the reason. Yeah.
Yeah. So
okay.
very nice to have you here, sir, for
Thank
the
you.
session. So with your permissions, let me have a short introduction of yours with the participants. Yeah, thank you, sir. So, dear participants, we have Mr. Sanjay Kumar with us. He is the founder of Telcolearn Services, and with his company, he is also engaged with the academicians on the recent research and development on 6G and beyond 6G technologies. And he is also working as an advisor with few tech startups on a pro bono basis. And he has more than 22 years of experience as an entrepreneur and senior management professional across startups, IT, telecom, and consulting with a successful track record in strategy development and execution, building building the partnerships, growing business multiple times, and growing new businesses from a cold start. As a 5G and cloud expert, he has trained more than 20,000 telecom professionals in more than 50 countries and 100 plus cities in India on 5G radio and core. So he was also an AWS certified solutions architect associate, and an AWS authorized instructor. He has delivered cloud training for many companies like Cisco, Nokia, Ericsson, Huawei, HFCL, Reliance Jio, Vodafone, Wipro, Accenture, and many others. So his mission is to support people in upskilling on telecom and cloud topics and to build innovative solutions that leverage the power of 5G and cloud. So let's welcome Mr. Sanjay Kumar and listen to him. So welcome, sir,
Okay,
and
great.
over to you.
Thanks,
You can
Soumya.
start with your yes, sir.
Yeah, great. Yeah, thanks, Soumya. Thanks, Mr. Arvind. Right, so thanks for the opportunity given. Right, so and thanks everyone for joining in. And we will be having a discussion around OpenRAN today. And OpenRAN, of course, we started with the discussion of disaggregated RAN, separation of hardware, software. But that's not really the only key areas what we need to look at the OpenRAN. OpenRAN, the real power of the OpenRAN comes from the implementation of artificial intelligence and machine learning, and that we will be, focusing on. This is going to be an overview session where we will be talking about the complete journey of the RAN architecture, how it evolved for some of the participants, talking about the 5G, the expectations around 5G, and how we are leading towards the 6G race, and how do we really actually fit into that game. That is what we are going to discuss in this session. Right. With this, I will just share my screen and do let me know when you are able to see my screen, and then we can continue with the discussion. Okay, is my screen visible?
Yes, sir. It is perfectly
Okay,
visible.
great. So let me just to save the bandwidth for everyone. Let me stop the video and let me start the session. Give me a minute. Okay. A minute. Okay, so this session is going to be about OpenRAN fundamentals and evolution towards 6G. We all know that OpenRAN has been a pretty hot topic in the recent past, and the kind of expectations what we had from the OpenRAN, it was not able to fulfill those requirements. And we will also talk about whatever the major reason behind that, and what do we really expect when we are evolving towards 6G. What I feel is Open RAN or the Open Radio Access Network is going to be one of the major fuel in the evolution of the 6G network, and that's why we have taken this topic for the day one. Of course, I have some more sessions which are planned in the upcoming days where we will be talking about more AI ML use cases in telecom and 5G and 6G network, and where we will also do some hands-on. We will see some kind of algorithms, machine learning algorithms which are building for the telecom use cases, and how do we really implement those things in the real network, right? So in this session, we are going to talk about evolution of 2G to 5G network. This is something we are going to, one second. I think there is something wrong with my, like annotation tool, right? We are going to talk about mobile network architecture. What are the different building blocks of a mobile network? I'm sure most of you have already gone through these details, but just to bring everybody on the same page, we are going to talk about mobile network architecture. Then we are going to talk about various standardization specification bodies, which include 3GPP, ORAN Alliance, Telecom Infra projects, and the things related to that. We'll also have a quick overview of the 5G network and the expectations from 5G network. And then we will talk about RAN architecture evolution, how the radio access network has evolved over a period of time, which were earlier given as a black box to the operator with a very, very minimal innovation. And most of the innovation which is happening today is happening in the radio access network, right? We'll also talk about 5G and our protocol stack, both from the control plane perspective and the user plane perspective, and what are the different split options we are designing to support the Open RAN architecture. And finally, we will talk about Open RAN architecture, different building blocks of Open RAN architecture. We will talk about Open RAN market players, what are the different companies who are playing into this market, and then what are the different innovation which are happening, in the 6G field from the open-end perspective. Now, just to Soumya has already introduced myself, but I'm working with a company called Telco Services. I have around 23 years of work experience. 18 years I've spent into training, worked across all the technologies, starting from wireline network till 2G, 3G, 4G, 5G, worked with transmission, IP, packet core, circuit core, and various vendor products I've worked with, which are Samsung, Nokia, Ericsson, ZTE, Cisco, etc. Now, talking about history and evolution of 2G to 5G network. And now when we talk about it, just give me a second, there is something, okay. Right, right. So if we look at the journey from 1G to 5G network, we have seen that we started with a very, very low data rates of 10 kbps, which started somewhere around 1980s in the first generation of network. And today in 5G, we are talking about 20 or 10 Gbps data rate. 20 to 10 Gbps data rate, 20 Gbps in downlink, 10 Gbps in uplink. And we are expecting these data rates to become at least 10x in the 6G and future network. Now, how do we really talk about the generation? And if you look in the past, majorly whenever we talk about the next generation from 1G to 2G to 3G to 4G, the major change which was happening was only happening in the terms of data rate. However, 5G is coming from a different perspective where we are not really looking at only end user or the human beings as a user, right? We are also looking for some new use cases which can generate new revenue streams or new market areas for the operators. So we are talking about not only the retail use cases or selling the SIM cards, we are also talking about a lot of use cases which are related to enterprise. And that's where the scenarios like network slicing, we talk about multi-access edge computing, we talk about 5G private network, all these things will fall in place. And these are the areas where we cannot really survive without implementing artificial intelligence and machine learning. So if I have to deploy, I have to make my network in terms of multiple network slices, and we have to have these slice resources to be allocated to the different slices. That can be done only with the automation, only with the orchestration, and that has to be completely powered with AI/ML. So these new features which we are talking about, multi-access edge computing, network slicing, those features are going to be literally dead without talking about AI, ML, and the things related to that. So even though when we talk about 5G, it is just the next generation we generally refer, but it is much beyond those traditional data rate kind of architecture where we are looking just higher data rate. We are talking about a lot of new use cases in 5G, and that is what going to pave the way for the 6G. Now, talking about artificial intelligence, if you look at the 5G architecture, and traditionally when we talk about 5G network architecture, the artificial intelligence, AI, ML comes as a flavor or a topping on top of 5G network. So 5G doesn't come with a native AI support. So it doesn't have the native AI architecture. However, what we are trying to do in 6G, and as we will discuss later, the 6G comes with a native AI architecture. So AI is going to be at the core of sixth generation network. Similarly, if we look at the traditional discussion happening around Open RAN, you will see there are two things what you will discuss, what you will see normally. The one thing which is going to be the hardware software disaggregation, where we are segregating the hardware and software and then using the general purpose processors or the COTS hardware. And the second discussion, what you will see is related to open interfaces, bringing in the interfaces like F1, which is happening between CU and DU, and the interfaces like front hall, which is between DU and RU. But Open RAN is not only. Hello? Any questions here? Okay, so Open RAN is not only about hardware and software disaggregation, it is also about bringing in AI ML as a secret sauce in the Open RAN ecosystem, and that's where the real benefit comes in. As we will see further, the Open RAN actually have the major target area as the AI ML, not really just the software and hardware disaggregation or the open interfaces. We are going to talk about all these things in the upcoming discussion. Now, but before we get into deep dive, let us have a look at mobile network architecture. And these are some of the basic building blocks of the mobile network, where we talk about access network. The access network is the part of the network which typically provides connectivity towards the end user. This is typically the air interface, and this air interface is also a very, very interesting area for the researchers, for the academician, like where you do a lot of things related to AI/ML, talking about channel estimation, talking about resource utilization, channel quality, and a number of things. And then within the access network, as we are building a lot of different blocks within the access network, which we will discuss later, like RU, DU, CU, and then we are talking about near RT-REC, we are talking about known RT-REC, we are talking about SMO, and that's where the real crux of AI/ML comes into the access network or the radio access network. The core and switching network are traditionally the networks which are providing the services, right? Where either they can have circuit switching services or they can have packet switching services. Starting with 4G, circuit switching is completely obsolete, completely scrapped. We are just living with the packet switching network. We're just living with the packet switching network, and that trend is going to continue in 6G as well. So 6G, the core network comes with it completely different architecture, where some part of the core network will be replaced, some part of the core network will be reused, and some can be enhanced, right? So there can be different type of network functions, network functionality, which will remain as it is, which will be enhanced, or which will be completely replaced in the 6G network. Of course, monitoring and supervisory networks, where we do the complete management of the network, which typically have the infrastructure like OSS, operation support system, where we talk about network operation center, NMS, OMCR, etc. And that's where we actually do the complete management of the network. Of course, transport network is also an integral part of the telecom network, which will enable you to connect the components within the access network, within the core network, and from the access network to the core network. So transport networks can be electrical cable, can be optical cable, can be satellite connectivity. Nowadays, NTN is another area we are focusing, where the end user can be served directly by the non-terrestrial network. So NTN is another interesting area. And recently, I was just reading one article today, R19, R20, which is release 19 and release 20, that are coming up with lot of enhanced feature on the NTN capabilities, right? However, in this session, our major focus is going to be on the access network part of it, where we will open this box, black box, which used to come as a black box to the operator. How we really open up, how do we really bring the innovation in the access network, and what is the implementation of AI/ML in this access network? That is something what we are going to discuss in this particular session. Now, what are the standardization and specification bodies? And I'm sure working with the telecom industry, most of you have already came across the ITU and 3GPP. ITU, International Telecommunication Union, and 3GPP, which is third generation partnership project. Third generation partnership project. So if we look at third generation partnership project, we understand that this was initiated, this was started when we started talking about third generation network. So the third generation network that happened somewhere around 1998, and that's where we have started talking about the third generation network, and we brought in a technology called as WCDMA, wideband code division multiple access, to implement our third generation network. So 3GPP was the body which has started creating 3G standards, but now it is not restricted to only 3G. It's not really restricted to only 3G. All the following generations like 4G, 5G, and even 6G, they are all managed and specified by third generation partnership project. So 3GPP, even the name suggests 3GPP, it is related to all the different generations from 3G to 4G to 5G, and also leading towards 6G. Now, there are two questions here. Now, first question is, and you can use the chat box to answer these questions. What was the first commercial release which was introduced by 3GPP? What was the first commercial release which was introduced by 3GPP, and what release is expected to be 6G? So what release number is going to be the 6G specification? You can use chat box to answer those questions, and we will discuss these things at a later stage. So what is the first release of 3GPP? What do you call that release? And what release is going to be the 6G release for the 3GPP? However, there are two more interesting specification or standardization body which have come into play. One is called as TIP or Telecom Infra Project. Other one is ORAN Alliance, Open RAN Alliance. Now, Telecom Infra Project was formed in 2016, 2016, right? And the idea was to create the open networks, the networks which can be open, which can be scalable. And one of the founding member for TIP was Facebook, Meta. So Facebook was one of the founding member of the Telecom Infra Project. And Telecom Infra Project is not only talking about Open RAN, they are also talking about open Wi-Fi. They are also talking about open transport network and things related to that. So Telecom Infra Project is a industry body where they talk about creating open standard for the next generation network. However, ORAN Alliance is the body which create the specification for the open RAN architecture. Now, there may be a question whether 3GPP or ORAN are they competing bodies or they are collaborating bodies. So the answer here is the ORAN Alliance doesn't really compete with 3GPP. They actually create their standards on top of what is already created by 3GPP. So basically, the ORAN Alliance doesn't work with the specifications which are prepared by 3GPP. They adapt those specifications, and on top of that, they create more specification. What do we mean by that? We are going to see that in the later discussion, where we talk about all these interfaces, where we talk about all these architectures and things related to that. Right? We will understand what is ORAN Alliance, what is Telecom Infra Project, what is 3GPP and ITU, and what actually they do. Right. So ORAN Alliance creates the standards which are not specified by 3GPP. So many of the things, many of the interfaces, many of the architectures are defined by 3GPP. ORAN Alliance is going to complement those architectures and going to add their information on top of it. Now, just to get an idea, ITU was founded in 1865, majorly talking about spectrum allocation, international connectivity, digital inclusion, telecom standards, and these kind of things. The 3GPP third generation partnership project established in 1998, and because of this, and the first specification they came up with happened in 1999, and that is why the first commercial release, as I have asked in the previous slide, is called as release 99, R99, and which is also referred as release 3. Right. So 1998, that's where we started talking about third generation network. But now it doesn't work only with the third generation network. It does everything from 2G and 5G till 5G and even going towards 6G network. The ORAN Alliance was created in 2018. So it's an industry group which creates interoperable standards, the standards which can interoperate with multiple vendors. Multiple vendors can create products just for the radio access network. Right. However, there were two basic, promises of Open RAN Alliance or Open RAN, that first of all, it is going to bring down the cost for the operator. And the second promise was it is going to ease the life of the operator. Are we able to meet those criterias or meet those objectives? That is a question mark. And why that is a question mark, we are going to talk about it. We will also talk about it. What are the challenges the open RAN industry which is facing today, and why we are talking about Open RAN can be a very promising technology in the 6G network. Now, if you look at it, the 5G was originally planned for year 2020. The original plan for 5G was 2020. And because of some push from the industry, they have to prepone it. So actually, we started standardizing 5G back in end of 2017. So it was a kind of preponement which has happened around 2 to 3 years earlier than what was expected. Now, by the time we have started creating standard for 5G, ORAN Alliance was just formed. So it did not get the maturity. What it should have got. And because of that, Open RAN was not able to make a dent into the 5G market. Even though it looks very promising on paper, it was not able to really make a great sense in terms of 5G deployment. By the time Open RAN standards were mature or they were ready to deploy, the 5G, major 5G deployments has already started happening. And that is the reason Open RAN was not really able to make a big difference into the 5G world. However, the 6G is still 5 years away. The original plan is IMT 2030. So we are expecting this 6G to come in somewhere around 2030. And I am pretty much hopeful that Open RAN is going to play a major role into the 6G deployment. So having these flexible multi-vendor, vendor, no vendor lock-in networks with the power of AI ML, power of different type of hardware, different type of software, different type of AI ML algorithms, OpenRAN is going to be a front runner in the 6G deployment. However, what the standards are created by the ORAN Alliance, but the industry movement is taken care by the Telecom Infra Project. So what Telecom Infra Project does, they run some kind of plug fest, they bring the industry together so that they can do the interoperability testing. They have some kind of labs, OTIC labs, etc., where they can do the functional testing, they can do the interoperability testing. They bring the whole industry together so that they build the open network deployment more affordable and available worldwide. So MET, the Telecom Infra Project, is majorly doing the industry phase of it, where they bring the industry stakeholder together and do the deployment, do the testing and things related to that, where ORAN Alliance does the internal work, create the standards, specifications. All these things you can find at a website which is called as o-ran.org. Now, moving on to the next topic. This is how the overall industry looks like. So talking about ITU and 3GPP, 3GPP have some kind of cross reference from the Wi-Fi, broadband form, etc. It works with a lot of 5G projects which are running in different regions. It works with a lot of 3GPP market players. So some problem with my notation tools, pardon me for that. And then this 3GPP is a collection of different bodies. So from EU, it is ETSI. From Japan, it is ARIB and TTC. Korea, it is TTA. China is CCSA. And from India, we have TSDSI. So TSDSI is contributing to the 3GPP initiatives, 3GPP standards from the India perspective. So TSDSI, Telecom Standard Development Organization, is actually contributing to the 3GPP standardization from India. Now, if you look at the open RAN architecture or open RAN standardization, as I mentioned, there are majorly two bodies. One is ORAN Alliance. The ORAN Alliance does the specification part of it. So they have a lot of working groups. Some of them are working with the hardware. Some of them are working with the interfaces, AI, ML, network management, ORAN network, ORAN slicing, etc. So they create the standards and the interfaces which can be multi-vendor and can have open softwares, multi-vendor and open softwares. However, the TIP or the Telecom Infra Project does the COTS hardware definition and create the reference products. COTS hardware definition and creates the reference products. They also, as I mentioned earlier, they also organize some kind of plug fest where they bring all these stakeholders together and then try to do the interoperability test. They also organize one of the event for the open RAN infrastructure called as Fuse, right? Fuse, they recently organized it. However, the software part, they have collaborated with the Linux Foundation, where they have created a ORAN SC or Open RAN software. Just allow me a minute. Let me stop my other applications so that we can actually, maybe some problem with my laptop, getting some issues. I'm just closing some of the applications so that it may be little better when I'm doing the annotation. Sorry for this interruption. Okay, so TIP, the open and software community, is actually doing the creating the open source softwares, open and interfaces, and they also talk about RAN intelligence. What is the RAN intelligence? We have some components called as RAN intelligent controllers, and that's where the actual power of, if you ask me, what is going to be the most powerful thing in the open RAN architecture, open RAN ecosystem, the answer is going to be REC. Answer is going to be REC, where they come up with some kind of application called as XApps, RApps, and we are going to talk about most of these things in the upcoming discussion. In addition to that, these bodies also collaborate with GSMA, ETSI, and also actually, they also have an open and policy coalition, which typically interacts with other organizations, and they help these government, these regulatory bodies to create policies around open RAN. Now, let's move on and let us talk about how the radio access network has evolved over a period of time. The radio access network, and as I mentioned, I come with around 23 years of experience in the telecom world. And initially, when we started, there used to be a very big rack with lot of plug-in units, with lot of wires, and you need a lot of technical skills to install a base station, right? And this is how it used to be. So basically, this one rack used to have lot of plug-in units, lot of front cables, lot of back planes, and you need a real technical skills. You need a lot of technical skills to install it, commission it, operate it. However, this used to come with a lot of logistic problem. So for example, if I have to look at this kind of rack, this kind of rack will come in the size of a fridge or a refrigerator. And the usual weight for this particular rack used to be somewhere between 200 kilograms to 300 kilograms. So installing this rack, managing this rack itself was a task, right? So you need a specific room with a proper air conditioning to install this rack. Over the period of time, we started moving away from these racks to some kind of modules. So we have moved to a modular architecture. We have moved to a modular architecture where we have started dividing the pieces of this rack, not the complete rack, but some specific functionality of this rack into some specific modules. These modules used to weight around 20 to 30 kilograms, 20 kilograms to 30 kilograms. They were easy to deploy. You can install it anywhere in the rack, out of the rack, maybe on a tower itself, on a mast, maybe in the open environment. And these these modules were having no plug-in units. So every time, whenever you face a problem, you can't really do any troubleshooting on the site. On the site, you just need to replace the modules. And because of this, your troubleshooting became very fast. Troubleshooting became very fast. So earlier, for example, in this case, I need to carry 10 to 15 spares, 10 to 15 spare units. But in this case, I just need to carry two spare modules. One is the radio module, one is the basement module. So my troubleshooting, my site restoration time, outage time were drastically reduced when we started working with these modules over the period of time. What else we did was, starting from the shelter house, we moved to the tower mounted. These are typically called as, initially, they are called as RRUs or RRH, remote radio units or remote radio heads. Remote radio units or remote radio heads. And these are the units which can be installed. These can be units which can be installed very close to the antenna. This gives us two benefits. What are those two benefits? The first benefit is, because this is installed very near to antenna, there were no feeder losses. Earlier, the feeder cables, which used to be very, very thick coaxial cable, used to go from the base station till all the way to antennas. Antennas used to be on a tower which used to be 40 meters, 50 meters, and there were huge feeder losses. Because these units are installed very next to the antennas, there are no feeder losses. You just install a 1 or 2 meter jumper cables and your feeder losses can be completely eliminated. The second benefit we get out of it is that you can save a lot of space in the shelter, because nowadays most of the towers are not really used by one operator. They are used by multiple operators. Multiple operators are using the same base station or same tower. And because of that, they have a space crunch in the shelter. So shelters are full of lot of equipment. So you don't have any more space in the shelter. So what you can do now is, instead of installing everything in the shelter, you can install lot of these things on the tower itself. So it will save a lot of space in the shelter. At the same time, it will save it will minimize the feeder losses. And that is why these kind of architecture become very popular. And sometimes we also refer it as a DRAN or distributed RAN, where my BBU is centralized, baseband unit is centralized, and my radio units are spread across the sectors. They are installed on tower or mast or poles or things like that. Now, also, earlier these racks used to come from the specific OEMs. Later, we started installing these things into the standard 19-inch rack. So moving away from proprietary rack to standard 19-inch rack. The real breakthrough came when we started talking about COTS hardware. COTS, which is commercial off the shelf hardware. COTS, commercial off the shelf hardware, which is typically a general purpose processor which can be used for deploying any applications. And what does that mean? Traditionally, all these things, what you see on the left side, they used to come from the specific OEM. That means all the hardware, all the software, they used to come from the same OEM. So same operator, the operator, you have to use this complete radio network from a single OEM. They cannot buy hardware from someone else. They cannot buy software from someone else. With the architecture where we talk about vRAN, as we will discuss later, virtualized RAN, what we have done is we can say that, okay, I need not to buy the hardware from the same OEM. I can buy the hardware from some other COTS hardware provider, which can be Dell, HP, or any Taiwanese company. And then on top of that, I can build the applications. I can build the application which is coming from either Ericsson or Nokia or Huawei or things like that. Right. So basically, these allowed us to segregate the software and hardware. And please note, this vRAN may not be Open RAN. Open RAN has a slightly different definition, and we will talk about that in the next few slides, where we will talk this complete journey where we talk about traditional RAN to the DRAN, CRAN, or talking about vRAN, virtualized RAN, and finally moving towards the Open RAN. Right. So this is the kind of evolution what we have seen in the hardware side of it, how hardware has evolved over a period of time to fit into some kind of COTS architecture. And now we will talk more from the perspective of the interfaces and the standards and specification. And now, because of these architecture, we need not to have specific hardware sitting on each and every site. Of course, we need a part of it, but many of these things can be deployed on private cloud or even public cloud. So many of these network architecture, including the core network as well as the radio network, can be deployed both on the private or the public cloud. Now, before we talk about 5G overview, 5G services, network architecture, 5G network functions, however, we'll not get into so many details here. We'll keep it very, very high level. I would like to pause for a couple of minutes, and if you have any questions, we can take those questions. Do we have any questions from anyone before we continue? Any questions? I hope you are able to hear me. Yeah, please go ahead.
Good evening, sir. Sir, can you please explain about the ORAN Alliance, like how it prepared their own standards and all? Like,
Yeah. Okay. So how can you please elaborate? What do you mean by how it does that?
like you have mentioned that it doesn't work with like whatever it prepared by 3GPP, and you have mentioned that it will be prepared by their own standards, right? So can you please explain it again, sir?
Yes. Yeah. So when
Thank
we
you.
will talk about open and architecture, in that we will clearly identify what are the things which are defined by 3GPP, what are the things which are defined by ORAN Alliance, and that will make a lot of sense there. So just bear with me for some time, and I think that will answer your question. Is that okay?
Yes, sir. Thank you.
Okay, great. Now, if you look at traditional, the starting point of 5G. Now, if you look at 5G, uh, till 4G, we were, yeah, Mr. Dr. Suman, please go ahead. Dr. Suman, would you like to ask something? Or it was you who has already asked this question? Okay, no problem. So traditionally, 2G, 3G, 4G, they talk about higher data rate, and we majorly focus on mobile broadband, MBB or mobile broadband. However, that is one of the key area even for 5G. So initially, 5G is designed with three different service verticals. One of that service vertical is enhanced mobile broadband or EMBB, which is nothing but just the extension of 4G network, which was providing 1 Gbps kind of data rate, and now we are expecting the 20 Gbps kind of data rate. However, in later versions of 4G, in release 12, release 13, we also talked about the technologies like NB-IoT, EMTC, which is called as narrowband IoT, enhanced mobile machine type communication. Those technologies were further enhanced, further elaborated with the introduction of MMTC. MMTC is called as massive machine type communication, where we are talking about supporting large number of devices with a deep penetration, and these devices can be very power efficient devices. These devices can be very power efficient devices. However, one of the key area, and that is also evolving with lot of new use cases, and that is where operators are the telecom industry is trying to make lot of sense in terms of 5G is URLLC. The URLLC or ultra reliable and low latency communication. Ultra reliable and low latency communication. And these are the use cases which we are talking about. They were not possible with the previous generation. So mobile broadband was possible but enhanced. MMTC was already there in one form or other, but the data rates, sorry, the latencies and the reliability what we are looking at in the URLLC was not possible in the previous generation. So URLLC is one of the key area or the key promise of the 5G network. At a later stage, if we talk about the future releases, release 16, release 17, we have also introduced some of the new verticals. For example, in release 16, we have introduced V2X, vehicular to X communication, which was earlier part of the URLLC. And in release 17, we have also introduced something called as HMTC, high performance machine type communication. That is again a subset of the URLLC kind of architecture. Now, the biggest challenge here is in EMBB, we are looking for a 20 Gbps data rate. In MMTC, we are looking for a million devices to be connected to the network. In URLLC, we are looking for a less than 1 millisecond kind of latencies. How it is possible to achieve all these things in a single network? And that is pretty difficult. So what we are actually trying to do in our network, that we divide this one physical network into multiple logical network, and where every logical network is called as network slice. So basically, network slice becomes a mandatory feature for the 5G network. So in 5G network, we can have multiple slices. A single user can access multiple slices, and all these slices can be completely isolated from each other, and we can implement AI ML algorithm to do the resource allocation for these slices. So in our demo, what we are going to see in the following sessions, we will also see how do we really define the resource allocated for every slice. And when we talk about it, we will see, okay, what are the actual value of, what is the predicted value of this, and what are the actual resources given for these slices. And we have to fine tune those algorithms so that we can have better and better resource allocation for these network slices. So network slicing is one of the key criteria, key parameter for the 5G network. Now, I'll not talk much about it. This talks about the the complete evolution of 3GPP, starting from release 9, going up to the release 16. So release 15, this is the place, sorry, release 15, that is where we have introduced the first release of 5G. We also call it the 5G phase 1. Release 16 is called as 5G phase 2. So release 18, release 17 is still 5G. Release 18 is called as 5G advanced. Release 19, release 20 are still continue to be 5G advanced. And we are expecting release 21 to be the 6G release. Recently, 3GPP has already released the 6G logo as well. So release 21, release 21 is going to be first commercial 6G release, first commercial 6G release. And people ask as of now, a lot of people ask this question, hey, do we really need 6G? 5G itself is not really used. 5G itself is not really a success. Are we going to see 6G in the networks? Are operators going to deploy 6G networks? Are OEMs going to build the products related to 6G? A lot of these questions are floating in the market, and you may come across some of these questions. But my take is slightly different on this. I say 6G may come sooner than expected. That is one statement I normally make. And it may not be the pure technical reasons. It may be some of the political reasons. Nowadays, there are government, there are countries who are pushing very hard to roll out or to actually standardize the 6G network. So every country have their own, alliances. Bharat 6G Alliance, they have NGMN, they have NextG Alliance, and Hexa Group in Europe. There are a lot of different organizations that are working on these specifications, and it may come sooner than expected. That is one. Secondly, the thing what we see here is, even though 5G was not able to deliver what it promised, but it may happen many of these things what we are discussing in 5G may become the reality in the 6G. For example, artificial intelligence came as a topping in the release 15 or maybe in the 5G, but it may become a major backbone of the 6G network. So I'm expecting that 6G is going to be another, groundbreaking technology. It's going to be even more successful than the 5G network. Whether this will happen or not, that only time will tell. But I feel that 6G is going to be a very, very promising technology, and it will be a very fruitful technology for the communication world. Now, if you look at the 5G course, I'll not get into the details, or generally in my training programs, I talk about all these network functions, the call flows, the identities, and things related to that. I've created a lot of videos on many of these topics related to open and related to network entry, PDU session, IMSI attach, registration, etc. And I will be sharing my YouTube channel link. If you want, you can refer to that YouTube channel as well. So, but these are the different network functions. So what you see on the top, the multicolor boxes, they are the various 5G core network function. In the user, they are all control plane part of it. They are all control plane part of it. In the user plane, there is only one network function, which is called as UPF, user plane function. In the radio network, as of now, we see only one box, and that one box is called a G node B. We also refer this as a 5G NR, 5G new radio. And at a later stage, we will see that when you double click on this G node B or 5G radio network, what are the different components you will see here? And that is going to be the discussion in the upcoming slides. Now, let us talk about RAN architecture evolution. Now, traditionally, these networks started with the plug-in unit based architecture. So initially, when I started my career back in 2003, first time I looked at the GSM base station, it looked like this. A lot of plug-in units, with lot of cables, front cables, back cables, backplane cables. So it used to be very complex architecture, and you need a lot of, so whenever you want to make this base station up and running, you have to go to the site, you have to, sorry, you have to make all these connections, you have to make a lot of configuration, you have to connect your laptop to these devices, make a lot of configuration, and then only it can be up and running. A single cable is wrong, you will have a lot of call drops. So this was very complex, and you need a lot of technical expertise to actually install and commission these kind of base station. This equipment, what you see on the screen, is called as Nokia UltraSite BTSs. I traditionally started my career with the same kind of base stations. Over the period of time, in the Nokia, we moved to some kind of modular architecture, which is called as Flexi BTSs, where we have a unit which is called as baseband unit, and there is another unit which is called as either RRU or RRH. RRU stands for remote radio unit. RRH stands for the remote radio head. So these remote radio units can be installed closer to the baseband unit or can be installed closer to the antenna. So you can have different type of architecture where you can install these radio units closer to the baseband units and closer to the antenna as well. And depending on the different type of architecture, you can use a different position for these type of units. However, when we have separated the BBU and RRU, when we have separated the BBUs and RRUs, what we can do is the BBUs can be in a centralized location. So all the computing resources are generally in the baseband unit. All the computing resources are generally in the basement unit. And what you can do is you can actually centralize all these things in a single location where it can serve multiple remote radio units. And these remote radio units can be connected to the BBU by using an interface called a CPRI interface, Common Public Radio Interface. So this is some typo error, not a private, but a common public radio interface. Common public radio interface, which was actually originally designed as an open interface. So there is a catch here. Even though CPRI was originally designed as an open interfaces, but it was not implemented like that. So most of the vendors, when they did the implementation of CPRI, they did a closed or vendor specific interfaces. So even though it was a open interfaces initially, it became a closed interfaces where you cannot have BBU and RRU from different vendors. Even though they were separated, still you have to buy the BBU hardware, BBU software, and remote radio unit from the same vendor or same OEM. So you have to buy all these components of the radio network from the same OEM. And that is what actually we want to break in the Open RAN. So in Open RAN, we want the BBU hardware, BBU software, remote radio unit, everything we can buy from the different OEMs, different original equipment manufacturer. And that's what we are trying to do in the Open RAN architecture. That's what we are trying to do in the Open RAN architecture. So this kind of architecture is called a CRAN or centralized RAN. Later we move to vRAN or virtualized RAN. That is where we have started using a different hardware or the COTS hardware for our BBU. Please note, it is only for the BBU. The BBU applications and the remote radio units, they still come from the same vendor. So basically what you see here is the BBU hardware comes from a different vendor, BBU software comes from a different vendor, but this interface is still a closed interface. Still, you have to buy the BBU software and the remote radio unit from the same OEM. So virtualized RAN may not be the Open RAN. Virtualized RAN may not be Open RAN. Open RAN is generally the virtualized RAN. Open RAN is generally virtualized RAN, but it is not mandatory that virtualized RAN will also be the Open RAN. So all these things till this time were completely managed, specified by 3GPP. 3GPP was handling all these things as a single entity. And that's where, okay, not this one, so disaggregated RAN, where 3GPP has also defined one more thing here. So if we see here is, the BBU is further broken down into two pieces. The BBU is further broken down into two pieces, and these are called as CU and DU. CU is centralized unit, DU is the distributed unit. CU is centralized unit, DU is distributed unit, and they have created an open interfaces between them, and that open interface is called as F1. F1 was the interface which was defined by CU and DU. Who has defined this interface? Not Open RAN Alliance. The F1 interface was specified by 3GPP. The segregation of CU and DU or dividing BBU into two parts, which is CU and DU, was done by 3GPP, was not done by the ORAN Alliance. So even though you've done this architecture, here there is a possibility where we also talk about open front hall, and that will actually lead to our Open RAN architecture. This is open front hall. As soon as we make this open front hall interface as an open interface, that is where we will lead to the intelligent and open RAN. Now, this is where the ORAN Alliance comes into play. So ORAN Alliance doesn't talk about this function, this architecture. Open RAN Alliance, ORAN Alliance, talks about the open front hall and lot of other interfaces what we are going to see in the next few slides. Please note, this is not really the complete architecture of the Open RAN. This is not the complete architecture of the Open RAN, and we will see the complete Open RAN architecture in the following slides. This is just referring to the previous discussion where we can have the EPC, 5G, or OCU, because now these CU, centralized unit, and DU, distributed unit, are compliant to the ORAN Alliance standards, and that is why we call them OCU, ODU, ORU, etc. Right. So all these things came into play when we started talking about ORAN Alliance. Now, before we start talking about ORAN Alliance, before we start talking about ORAN Alliance and the Open RAN architecture, let's have a look at the 5G NR protocol stack or NG-RAN protocol stack, both from the control plane and the user plane perspective. And then let's talk about split option, which will actually lead to the Open RAN architecture. Now, without understanding these 5G NR protocol stack and these split options, we will not be able to reach to a conclusion, what RU does, what DU does, what CU does. After understanding these only, we will be able to comment on this. That's why this discussion is pretty important. Now, if we talk about the control plane part of it, the architecture looks more or less the same as we used to have in the 4G network. So we have a PHY layer at the lowest layer, then we have MAC layer, medium access control, RLC radio link control, PDCP packet data convergence protocol, or RRC radio resource control. Please note, these are not really the new layers or new introduction in the 5G world. This is more or less the same structure. I'll not say the same content, but overall structure remains more or less the same what we used to have in 5G. On top of this RRC layer, we have a NAS protocol called as known access stratum protocol, which typically communicates between the UE and the core network. So in the core network, the entry point is AMF, access and mobility management function, and that is where our NAS protocol runs. Now, if we look at the user plane part of it, there is a minor difference. In case of 4G, we used to have protocol only till PDCP. So if you look at these four lower layers, they are common for control plane and user plane. So the PHY, MAC, RLC, and PDCP, they are normally the common layers. They are normally the common layers for normally the common layers for both control plane and user plane. There is one new layer introduced, and that new layer is called as SDAP layer. SDAP layer, which is called as Service Data Adaptation Protocol. Service Data Adaptation Protocol, which is majorly related to the quality of service, where we can allow multiple QoS flows, which can be mapped to a single radio pair. We will not get into the details of this. If you are interested, maybe we can discuss it offline. You can ping me later and I can try to answer it. But SDAP is majorly used where you want to map multiple QoS flows. So this is basically to implement a new way of quality of service. So it is a new way of implementing quality of service that is enabled by SDAP or Service Data Adaptation Protocol. So this is a new layer defined in 5G, which was not present in the 4G in the user plane part of it. But if you look at the overall protocol stack, only this is the difference. The control plane protocol stack remains as it is. The way it was in the previous generation, it remains as it is in the 5G itself. On the user plane side of it, towards the core network, we have GTPU or GPRS tunneling protocol for user plane. Now, what we have done here is we have brought all those layers together, brought all these layers together, and then further divided these layers into some different parts. For example, phi layer here is divided into two parts, low phi and high phi. Low RLC, low MAC, high MAC, low RLC, high RLC, and then we have PDCP, which further connects to RRC or the SDAP protocol. Now, traditionally, when we have done the separation of the BBU and RU, if you remember from the early days when we did the separation of BBU and RU, they were typically giving all the functionality to the BBU. Only the RF functionality was given to the RRU, and this was considered as option 8. So option 8 was the traditional option what we were using, and that's where we had done the separation of the BBU and RRU. So RRU was just taking care of the RF part. However, doing this have its own challenges because CPRI also comes with lot of limitations. So what we have done here is we have created multiple options starting from option 1, going up to option 8. Starting from option 1, going up to option 8, and the most popular option for the open-end architecture is called as option 7.2. Option 7.2. 7.2 means we provide the low phi functionality and the RF functionality to the RU. So the low physical layer functionality and the RF functionality to the RU or ORU as such, and starting from high phi till high RLC. So complete layer 2 functionality, which is high phi, low MAC, high MAC, low RLC, high RLC is given to the DU or distributed unit, and the PDCP and RRC functionality is given to the CU. So layer 3 functionality is given to the CU. Layer 2 functionality is a part of layer 1 functionality is given to DU, and only the low phi part of it is given to the RF. That is not really the end of the story. Because this option 7.2 is also having two different options, which is called as 7.2a and 7.2b, with the minor differences related to pre-coding implementation. So pre-coding can be either in the DU or in the RU, depending on 7.2a or 7.2b, but as of now, we'll not get into those details. So basically, most of the open-end architectures we talk about, they normally refer to the 7.2 split. 7.2 split means the low phi and RF is given to RU. Anything above high phi till high RLC is given to DU, and PDCP and RRC is allocated to the CU or the centralized unit. And that's what actually the building block of your open-end architecture. Now, let's move on and start talking about open-end architecture. But before we do it, I would like to pause for a couple of minutes and take up any questions if we have. Any questions from anyone before we continue? Okay, yeah, Dr. Suman, please go ahead. Hello?
Yes, sir. Yes, sir.
Yeah, please go ahead. I see your hand was raised, so that's why I thought that you have a question.
Okay, Mr. Ankush Gupta, is there any query?
I see there is a hand raised from Anita as well. Anita, can you please ask your question?
Please mute yourself. If you do not have any question, then please mute yourself.
No problem. I see there are some people who have raised their hands, so I thought that they have a question. That's why I wanted to ask that question.
Okay. Okay,
Yeah, no
it's
problem.
better that if your mic is not working, participants, if you want to ask anything and if your mic is not working well, you can drop your queries at the chat box.
Yeah, so
At the end of
yeah,
this
so what we
session,
will do is
we will
at
take
the
all the
at the end
queries.
we will
Yes,
take all
yes,
the
yes.
questions. Yeah, that's correct.
Yes,
Yeah, that's correct.
after this
Okay, no
session,
problem.
we will make 5 to 10 minutes for the question answer round, and in that we
No
will
problem.
address each one of the queries. Okay,
Sure, no problem.
is it fine with
Let's
you,
do that.
sir?
Yeah,
Yeah.
I'm good with that.
Yes,
I'm good with that. Yeah.
yes.
Right.
Let's continue then. Yes, sir.
Yeah, so this is where we actually, this picture itself comes from the ORAN Alliance, right? So where we actually create the open and architecture. Of course, it looks very now what you see here is the same G-Node B what we used to have, the same G-Node B what we used to have as a single box is broken down into so many pieces, right? And if you look at this picture, there are two different colors what you see in the lines, two different colors what you see in the lines. The first color is the these yellow interfaces, or I'll say the bright yellow interfaces. The other one is these blue interfaces. Right now, this was one of the questions which was asked. So most of these blue ones, what you see in this particular site. Sorry, my annotation tool is not behaving properly today. Sorry for that. But these blue part, what you see here is that those interfaces are typically defined. Those interfaces are typically defined by the 3GPP. They're typically defined by the 3GPP. I see some noise. Can you please mute yourself? Okay. Now, Dr. Soumya, can you please mute the person who is on the speaking now? Okay, right. So the green ones or the yellow ones, what you see here, they are mostly defined by the 3GPP. Okay, let me explain this from a different picture. So this picture comes from the ORAN Alliance. And now what you see here is we have the SMO, the Service Management and Orchestration Framework, which also includes the known real-time rig. And we normally call it as known real-time rig. And then we have near real-time rig, near real-time radio intelligent control, RAN intelligent controller. Then we have CU, which is the centralized unit, which is further divided into two parts, which is called as OCU CP and OCU UP, which is nothing but the separation of control plane and user plane functionality. And then we have ODU, the distributed unit, RU, the radio unit, and then we have something called as O cloud. Right. Now, let us talk about all these things one by one. Let us start from the bottom. O cloud. O cloud is nothing but a COTS hardware or general purpose server. It is general purpose server which can be used to host multiple of these functionality what you see in the upper layers. So it can be used to host your ODU, your OCU CP, OCU UP, or your near real-time rig, or a combination of these things. So I can have a common purpose hardware which can be used to host your ODU, your OCU, your near real-time rig, etc. Right. So basically, this O Cloud server is nothing but a server which can be used to host one or more applications of the ORAN ecosystem. The ORU is generally a physical network function. Our other network functions can be VNF, virtualized network function, or can be CNF, containerized network function. But ORU is majorly a physical network functions, and that is how it is going to transmit and receive. However, the ORU communicates with the ODU with the CUS and M plane. CUS stands for control, user, synchronization, and M stands for management plane. So the complete management of the radio unit, and also all the data related to which has to be sent to the user is transferred from the DU to RU or from RU to DU using this CUS plane or M plane. CUS stands for control, user, and the synchronization plane, and M plane stands for management plane. In addition to that, we can have alternative management plane, which can directly come from the SMO or service management and orchestration. The interface between OCU-CP and OCU-UP, OCU-CP and OCU-UP, they are typically the F1 interface, OCU-CP to OCU-UP to the ODU, called as F1C and F1U. And if you look at the color, they are typically the interfaces which are defined by 3GPP. So what I'm trying to convey here is the architecture, what you see here, all the gray color or the black color lines, they are the interfaces which are defined by 3GPP, All the green color lines here, they are the specifications or the interfaces which are designed and defined by 3GPP. And that's what I meant. When I was talking about that ORAN Alliance doesn't compete with 3GPP, they actually complement. So they don't really touch the interfaces which are defined and specified by 3GPP. They adapt to those interfaces just like that. And then build other interfaces which are actually not defined or specified by 3GPP. Right. Between OCU-CP and OCU-UP, we have another interface called as E1 interface. That is again defined by 3GPP. I will not talk about these XN, X2 and NG interfaces because they are mostly toward other G node Bs or the core network, right? Between near real-time RIC, we have, and these components, we have an interface called as E2 interface. So the E2 interface is the interface which is coming from the near real-time RIC to the CUCP, to the CUUP, and to the ODU, right? And the near real-time RIC gets its information from the non-real-time RIC with an interface called as A1 interface. So A1 interface helps the non-real-time RIC to share the trained model and any non-real-time data with the near real-time RIC, so that near real-time RIC can deploy these things in the real-time manner or in the near real-time manner, right? Now, coming to the central piece of it, which is non-real-time RIC and SMO. So the non-real-time RIC, which is typically used for training your AI/ML models. So all the data what you collect from the different network functions has to be fit into a data lake. And on top of that, we will be running our AI/ML algorithms, or we will be training our models. And those training of the models happen at the non-real-time RIC or some adjacencies of this. So basically, you get a lot of data from the network, run your algorithms, train your algorithms, and finally, after training those algorithms, you send those algorithms to near real-time RIC for the deployment. All these things in the near real-time RIC, they are called as accepts. So basically, in near real time, there will be multiple accepts related to resource allocation, interference management, and things related to that. In the non-real-time RIC, these applications are called as RApps. So if you want to do traffic prediction, if you want to have QoE implementation, all these things will be implemented in the non-real-time RIC as a R application. And in addition to that, we have D apps or distributed apps, which can be typically used for some real-time control, and they can be hosted in the CU or the DU. The SMO, or the Service Management and Orchestration Framework, is a larger picture, where we are doing end-to-end management of the network by using O1 interface. O1 stands for the OAM interface. OAM stands for Operation, Administration, and Maintenance. So by using this interface, the SMO is connecting to all the network functions like ORU, ODU, OCU, OCU, CP, UP, and near real-time RIC. And it collects the data, collects the operation and management data from all these network functions. At the same time, it gives command to manage these network functions. So basically, SMO becomes a central body to actually manage the life cycle of all these network functions in the architecture. Now, one question is about RIC. What is RIC? And this is one of the things which is completely new in the open architecture. If you see, we have already talked about ORU, ODU, OCU, etc. So RIC is the only entity which is completely new. So what RIC is doing? RIC is a kind of, a data analytics engine, or I'll say data analytics framework, what we have created, where we are trying to centralize our intelligence. Earlier, this intelligence was all distributed among multiple functions, multiple layers. We are trying to centralize this intelligence, create some insights about it, and then try to implement those actionable insights. That is what the real job of the RIC. That is what the real job of RIC, or RAN intelligent controller. So making your RAN intelligent, is the functionality, which is one of the motto of the open RAN architecture. Making your RAN intelligent, that is one thing which is implemented by the RAN intelligent controller, or RIC. Now, without getting into too many details, you can also look how this architecture between DU and RU looks like. These are the things in the CU plane, in the synchronization plane, where you either use precision time protocol or synchronous Ethernet. And how do we really manage the M plane, or the management plane part of it? I'll not get into too many details here because we have a limited time. But if you are interested, if you're working on some of these areas, some of these interfaces, this can be interesting discussion for some of you. Now, what are the different open and market players and suppliers? This is one of the most complex questions what people are asking today. Traditionally, we see there were initially three companies in the early days. There were three companies who have tried to make a difference in the open and market. These three companies were Parallel Wireless, LTO Star, and Mavenir. So Parallel Wireless, LTO Star, and Mavenir. Out of these three companies, Parallel Wireless has faced some challenges, and they have scaled down their operations like anything. So even though they are still active, still energetic, but they are not really going with this very aggressively. So even though Parallel Wireless is still into the game, but they are not going very aggressive on this. The LTO Star was later acquired by a company called Rakuten Japan, a company in Japan, the fourth largest operator, and they have acquired LTO Star, and they formed a company, another company called Rakuten Symphony, which is like an OEM. So LTO Star became a part of Rakuten Symphony. It became a part of Rakuten Symphony, and they are acting like an OEM, where Rakuten Mobile is an operator which is based out of Japan, which is the fourth largest operator in the Japan. The Mavenir is still the biggest stakeholder in the open and space, and they are actually driving this force further. The challenge which comes from the traditional vendors, the companies like Nokia, Samsung, Ericsson, who were the traditional RAN player. And today also, these companies and a few more companies like Huawei and ZTE, they actually have more than 95% of market share in the radio access network. So today also, the open and architecture, open and ecosystem is not more than 4 to 5%. Still, the 95% of the radio market is handled by these companies, and in addition to that, Huawei, ZTE, and a couple of other companies. So these are the companies which are typically running the market, running the radio access network from many decades. And this is going to be one of the major setback for these companies if open and become successful. However, even they have not stayed away from the open and world. They have built their own open and they have built their own vRAN standards, and they are also having lot of different products which can support open and architectures with some kind of star mark, right? So terms and conditions apply. So even though they are pretty much aggressive in the radio access network, they may or may not feel like getting into open and architecture. Just to take an example, recently AT&T has given a $17 billion $17 billion order to the Ericsson, where it says single vendor open end. Now, people were just asking, what does that mean, single vendor open end? If it has to be open end, it can be multi-vendor also. So that has gone to the Ericsson. So these are some of the incumbent player in the open end market. However, if you look at the companies who are a part of this ecosystem, the numbers are really huge. TIP have almost more than 300 companies as members, which includes the operator, the mobile network operator, which includes the OEM, which includes the various software companies, system integrators, hardware manufacturer, and a number of different companies who are the part of the TIP community. Even ORAN Alliance have a lot of different members, which includes the open and operator member, OEM member, software companies as a member. So almost every major telecom company in the world is part of Telecom Infra Project and the ORAN Alliance, right? In addition to that, they have something called as OTICs, which are Open Testing and Integration Center, right? So ORAN Alliance, where they have created some kind of open testing and integration center. And if you really want to know more about it, you can go to the o-ran.org, and they have a map. They have a map on their front page, on their landing page, where you can see where all these things are located, where the OTICs are, what type of activities they do. And what they typically do is they provide you badges like certificate, certified, interoperated, end-to-end tested. So basically, if you are building your open RAN products, either software or hardware, you can test and integrate them with the OTICs, and then you can get these badges, and that will help you to take those products to the market and to the end customer, right? What OTIC does is they basically award ORAN certification and badges. They host plug fairs, etc., without getting into too many details of the OTIC. Now, if we look at the overall ecosystem, of course, getting into a little more detail. So we have operators, which includes companies like Airtel, Dish, China Mobile, Jio, KDDI, Telefonica, Docomo, Rakuten Mobile, etc. Then we have system integrators. They are also becoming a very, very integral part of this open ecosystem. An interesting point here is the system integrators are the biggest beneficiary of this open RAN architecture. And why so? Why so? Now, if you look at it, the operators were traditionally not really interested in getting into the technical know-how of the network. They generally used to outsource all these things to the OEMs. However, now if they are bringing in a lot of different OEMs in their network, finally, the system integrators are going to integrate those networks together. And that's where the system integrator becomes one of the important part of the ecosystem. A lot of companies like Redis, like Nokia, Parallel Wireless, they build a lot of softwares related to Open RAN. Companies like Comba, JMA, they are building a lot of small cells. RRU, there are companies, Fujitsu, Comba, NEC, they're building a lot of RRUs and AAUs, which are called as antenna array units. And then companies like Dell, HP, Contron, Supermicro, they are building the general purpose hardware or DUCU hardware for the open RAN architecture, right? So do we have enough solutions? The answer is yes. Is the ecosystem healthy? The answer is yes. Whether it is going to make a dent or make a mark in the network, that will be visible in next few years. So even though as of now, it doesn't really look that promising, but I'm sure in the coming 2-3 years, it is going to make a big difference. Now, this is going to be almost at the end of the discussion, and then we will open up for the questions. And we will also have a quick assessment for all of you, online assessment, which you can participate. So 6G innovation for Open RAN. So as I mentioned, we are moving towards of the 6G evolution, which is release 21. So we are expecting 6G in the release 21, and the timelines of that will be defined in June 2026. So we are almost 1.5 years away from getting the 6G timelines. So as of now, they have defined the timelines only till release 20. So only till release 20, they have defined the timeline. 6G timelines are yet to come. However, in the similar pace, we are also expecting the 6G trials and 6G products for Open RAN. And if you look closely, this was one of the major setback for Open RAN in 5G. In 5G, the specifications were already hitting the market. The ORAN alliance was just formed. So The specification of OpenN came after getting the 5G specification, and that was the reason the OpenN was not able to make a difference in the 5G. But as we speak today, the Open RAN is also evolving in the parallel to the 6G implementation, or sorry, 6G specification, and that is why I am pretty hopeful that OpenN is really going to make a difference in the 6G deployment. So OpenN is also evolving along with the evolution which is happening towards the 6G in the 3GPP. Now, some of the usage scenario. Earlier, in case of 5G, we started with the triangle where we talked about EMBB, we talked about URLLC and MMTC. In 6G, it comes with a hexagon where it is extension of 3 existing services, 3 different services which are enhancing towards the immersive communication, hyper reliable and massive communication. But in addition to that, this comes with 3 more areas. One is called as integrated AI and communication, where AI is becoming a native part of the 6G architecture. ISAC, integrated sensing and communication, where sensing and communication is also integrating in the network, and ubiquitous connectivity, where we are talking about very seamless connectivity across all the network. And in addition to that, they talk about sustainability, ubiquitous intelligence, security, privacy, resilience, and connecting this image comes from ITU. This is typically talking about the usage scenario of 6G with the standard of IMT 2030, right? The KPI expectations of 6G, the KPI expectation of 6G, we are talking about user experience data rate, peak data rate from 20 Gbps going up to 100 or 1000 Gbps, which is 1 Tbps kind of data rate. The user experience data rate changing from 100 Mbps to 1 Gbps, 2 times the energy efficiency, the spectral efficiency 2 times, the latency is going to be 10 times less, 0.1 millisecond, which was 1 millisecond in 5G. Connection density going towards the 10 million devices per square kilometer. Reliability going from 10 raised to the power minus 5 to 10 raised to the power minus 6. So these are some of the KPI expectations from 6G network. Easier to share on the screen, very difficult to implement, and what type of applications we will have to actually use these kind of KPIs, that is still a big question mark. So even though these KPI looks very beautiful on the picture, on the slide, implementing these things in the network are going to be challenging. At the same time, do we have enough applications? What is the killer application we are going to have in 6G to actually consume these services? That is still a big question mark in the 6G network, right? So some of the survey that was done with one of the leading research company. What will you have in your 6G network? Is it going to be only 3GP specification or ORAN compliant solutions as well? So almost 80%, 80-90% people say that, okay, they are going to have a bigger stake of the ORAN components. What is going to be the priorities of the network layer? Integrated models, AI models across multiple layers, end-to-end implementation of the AI/ML. What tools will be needed in the 6G framework? So end-to-end service modeling, end-to-end tools, RAN design tools. This is another parameter. How will you handle security? Security is going to be very critical aspects of the 6G network. So they want this security to be available in the design phase itself. So from the day one, they are looking for the security features to be implemented in the 6G network. Now, what can be the 6G use cases, category of interest? And if you see out of all these things, this is the most important one. This is the most important one. They want artificial intelligence and machine learning in every part of 6G, every part of 6G. So this is the major interest area for the 6G use cases, right? What are the interested work area in the OpenN? And as I mentioned earlier, RIC or RAN intelligent controller is going to be one of the key area, and almost 50% interest comes from the almost 50%. Just give me a second. Sorry. Almost 50% interest come from these XApps and RApps ecosystem, which is typically a part of the near RT RIC or known RT RIC, right? The another interesting forum which was created recently is called as AI RAN Alliance. AI RAN Alliance have 3 different focus area. One is called as AI and RAN, another one is called as AI on RAN, and the third one is called as AI for RAN. So AI and RAN talks about asset utilization. How do we really share the same infrastructure? The infrastructure, the computing, the storage, the memory, what you're using, underlying infrastructure. How do you really share it between the AI and the radio access network? AI on RAN, bringing in new applications which can be enabled by the radio access network. And AI for RAN talks about AI for the enhancements of the radio access network. AI for the enhancements of so increasing spectral efficiency and having better channel estimation, better resource allocation. These are the applications related to the radio access network powered by the artificial intelligence. So these are the three key focus areas defined by the AI RAN Alliance. In addition to that, there is another forum which is created, another body which is created called as GTAA, Global Telco AI Alliance, where companies like T-Mobile, Etisalat, Singtel, SK Telecom, and SoftBank has come together, and they want to create a specific large language models. What is large language model? LLMs. We are going to talk about in the subsequent session, the future session, where we talk about AI, ML, Gen AI, deep learning, talk about Gen AI, large language models, etc. Where these 5G companies has agreed to develop a large language models that is specifically designed to meet telco needs, where they want to work in the areas like customer interaction, digital assistant, chatbots, etc. So these are the companies, they are creating these LLMs in the multi-languages like Korean, English, German, Arabic, Bahasa, and some other languages. So this is another interesting area, this is how the AI thing is happening, is unfolding in the telecom world. That will be interesting to see how these things will unfold in the next couple of years. So with this, I'm concluding my session. I will just open the floor for the question. And after the question, we will have a quick assessment and then we will close the session. So any questions from anyone before we move forward with the assessment? And please feel free to share your opinion where the session was okay, good, bad. And if you want, I can also roll out a, assessment form, and then we can take the assessment from everyone. Okay, if you have any questions, please drop your queries in the questions, sorry, in the chat box. I'm just sharing my, 1 second. Just a minute.
Yes, there is a query regarding the participant wants some more details on quantum communication for 6G.
Okay, give me a minute. Okay, so I just shared my LinkedIn profile in the chat box. So if you wish to connect to me on LinkedIn, you can do that. Now, this question comes from Dr. Jayanti. It says, please give some more details on the quantum communication on the for 6G. If you see, the traditionally the communication, the architecture, the application layer for telecom was completely different than the underlying infrastructure. However, as we move towards the hyperscale or maybe in the very, very fast kind of communication, and the kind of latencies we are talking about, the kind of computing resources what we are talking about, that is not really possible. That is not really possible with the traditional computing. So quantum computing is going to play a very critical role in the future generation of network, because with the traditional computing, these things are not possible. These things are very difficult to achieve. So yes, quantum computing is going to play a very important role in the 6G implementation. When it comes to very low latency, very fast processing, this becomes one of the interesting area. Another one, what is the role of Open RAN on 6G edge intelligence? Now, Mrs. Suman, if you see this, Open RAN and 6G edge. First of all, we need to understand the idea about what is edge computing. The edge computing has nothing to do with the radio access network. So basically, the applications the applications which has to be closer to the end user, and typically they can be deployed at the edge of the network. And in this scenario, the edge of the network is nothing but the radio access network. So what we need to do is we need to have a closer integration. We need to have a closer integration of the applications with the radio access network. And if you look at something called as third-party applications, so when you look at X apps, it says third-party applications, and some of these third-party applications can be deployed at the near RT rack in the form of edge applications, right? So Dr. Akanksha says, please suggest simulation tools for designing of the 6G network. So Akanksha, if you see, depending on what area you are working with, so if you are looking for majorly the file layer, etc., or the lower layers, you have MATLAB, lot of MATLAB related tools what you can use for 6G simulations, etc. If you're talking about end-to-end procedures where you can actually simulate things, those things are not available because these standards and the specifications are yet to be defined, right? There is another one related to cognitive radio. Another one is, one second, how to meet URLs in case massive data and 6G using FLSFL. So I'm not sure what is this FLSFL, right? So basically, the cognitive radio, cognitive radio are the radio access network, and specifically, if you look at the AIML implementation, that has majorly to do with the cognitive radios and the air interface, right? Uh, if you okay, this Suman says how to meet URLC in case of massive data. Suman, if you see the very first thing what we have seen in the discussion, that every time you cannot achieve all the things all the time. So if you want to have 1 Tbps data rate and at the same time you're looking for a latency of 0.1 millisecond, that may be practically impossible to achieve. So what we need to see here is we have to divide our network into slices. Where every slice will have their own KPIs. So every slice will have different service level agreements, different kind of key performance identifiers and things related to that, and they will remain to that slice only. So you cannot achieve all the things in a single logical network. Of course, it can be single physical network, but it requires a lot of different alteration, a lot of different changes to the network. Right. So with this, I think we can move to the assessment part. And before, one second, give me a minute. Let me. Dr. Suman, is that okay if we take an assessment?
Yes, sir. Yes, sir.
Okay.
It's your session. These are your listeners and your participants. Whatever you want to do to share the knowledge, it is allowed.
Okay. Let me do that. Yeah. Just give me a second.
Any intended goes live.
If Madam Gayatri, is any query from your side? Is any query? Then please unmute yourself. Yes. Otherwise, please keep your mic muted.
Okay, ma'am.
If there is any query, you are most welcome to ask the question. But if there is no query, then please mute yourself. Thank you.
Okay.
Yeah, just give me a second.
Meanwhile, you are looking for the assessment question, sir. I would like to share my personal review on your session. I have only one word. It is fabulous. It is fabulous. And the way dynamically you have explained the work areas and you handled the queries, sir, it is impressive. Although it is not my research area, but now I'm thinking to work in this.
Okay,
It's
great.
really,
So
it's really
yeah,
very
I've
good.
just shared I just shared one URL in the chat box,
Yes,
and just
yes,
try to click on it and see if you're able to open the question paper. It's a quick assessment, maybe will not take more than 5 minutes.
yes,
Just
sir.
see that if you're
Sure.
able to open it.
మీ దగ్గర అవ్వట్లేదు కదా నాకు.
Yeah, it is loading. I guess it will be open soon. It is MS form, right?
Yeah, it's MS form. Yeah, that's correct.
Yeah, fine. If you want it to be online, or you want the responses after the session?
So I think it will not take more than 10 minutes. If they can do it now, it's fine. Right? Otherwise, after this, it's also okay. Right? I'm okay with both. Right? So.
We will test the form, sir, after the session, and we will circulate among the participant, and I personally will collect all the responses. I'll check out
Sure.
and I'll return back to you. Is it
No problem.
is it okay with you, sir?
Yeah,
Thank
I'm
you
good
so
with
much.
that. Yeah.
Our participants have already sent some messages, but some, I think, missed sending you thank you message on the behalf
Yeah.
of an entire committee, organizing
Thank you,
committee. On the behalf of
Yeah.
all the participants, I would like to thank you so very much that you shared
Yeah.
such immense knowledge on 6G and beyond, and you made it clearly work very worthy for
Thank
all
you.
of
So I
us.
have two more sessions coming up. Two more sessions coming up.
Yes,
Right. So if I think the link is going to be the same for those sessions as well.
yes, sir, we will update you. If there is any change, we
Okay,
will update you.
that's okay. No problem. Right. So I'll just share that link with Mr. Arvind, and you can float it to the participants as well. Yeah.
Yeah, sure, sir, sure, sir.
Okay. Thank you very much.
Okay,
Thanks for your
thank you.
time, and I'll see you in the future sessions. Yeah. Thanks a lot.
Okay, sir. Thank
Yeah.
you. Bye.
Thanks. Bye. Take care.
So, participants, I hope you have really enjoyed the session. Now, next session, we are ready with the speaker, and let's welcome Dr. Sanjeev Sharma. So, very good evening. I would like to request you to turn on your camera and mic, please, sir.
Yeah, hello.
Thank you so very much for joining us.
Yeah, thanks.
I'm Dr. Soumya Goyal, and I'm welcoming you to the session on the behalf of the entire organizing committee, sir. And if you
Thank you.
allow, let me introduce your bio with the participant, with your permissions.
Yeah, thanks.
Yes, sir. So, participants, I would like to introduce you Dr. Sanjeev Sharma, who is working as an assistant professor in the Department of Electronics Engineering at IIT BHU Varanasi. He has done his PhD from IIT Indore in 2018, and he has done postdoctoral at Monash University, Melbourne, Australia. His current research interests are developing physical layer techniques for next generation wireless communication networks and application of deep learning to design wireless communication systems. And during his PhD, he has worked a lot on the sparse signal processing techniques for wireless communications. And we have such an immense source of knowledge right now. I hope you will enjoy and you will learn a lot from Dr. Sanjeev Sharma. So, sir, now I welcome you and request you to please start the session. The audience is all yours.
Okay, thanks, Dr. Soumya, for introducing me. Can I share my screen?
Yeah, sure, sir.
Yeah, thanks.
Please see. You can see, I guess. Yes, you have the sharing rights. Yes, your screen is visible to us.
Okay. So I'm just making full screen. Can you see now?
Yeah, there's a thank you and question slide, sir.
Yeah.
OFDM,
So
wireless communications, right. It's clearly visible and you are perfectly audible.
yeah, thanks. So good evening, everyone. So this session we will talk about some AI and ML application for wireless network design. Especially we will focus on the OFDM that is currently we are using in 4G, and we are also using them 5G, and we are also planning to use it in 6G wireless networks, or some advanced version of this waveform we will go into next generation wireless network. So this is the course outline that we will introduce what is the AIML. Okay, I'm not expert in the AIML, so I just briefly cover what is the AIML, like a basic, okay, and how people can use it for wireless communication network design, especially when we are talking about the channel estimation, detection, or like a resource management point of view, or handling the like interference issue. Then this AIML application, we will look especially in the OFDM and versus OTFS system. So maybe you know what is the OFDM, that is the orthogonal frequency division multiplexing. That is a wireless technology we are using currently in 4G and 5G mobile phones. And people are also exploring the new waveform, that is a orthogonal time frequency space modulation, orthogonal time frequency space modulation, that is OTFS. So what is the OTFS and how it differs from the OFDM, that we will look. Then we can conclude the talk. So whenever you have some questions, please ask. Okay. My screen is full screen mode, so maybe you are not visible to me. Okay. So if I lost connection or something, anything happens, let me know. Okay. So what is the artificial intelligence? Currently, if you're looking, everyone is talking about AI, ML. So AI is generally, if you can think, is a computer science technology. People are like talking about AI, artificial intelligence. So artificial intelligence meaning is that when you're doing some when you are designing the system, that system is capable itself to take the decision without the human intervention, or require very minimal human intervention. Then we can say that this is the AI enabled system. Okay, so system, we know system is a certain block function that performs some action on the some input or some task, then it produces some kind of output, so that you can understand. So AI enabled meaning is that this like a human intervention we are trying to minimize. That is the basically we can say that AI based system design. So that task include the reasoning, learning, then problem solving, and language understanding and decision making. These generally tasks we are including. So that is our day-to-day life we are talking about, or we are taking the decision that based on the reasoning, some kind of learning, some kind of problem solving, or some kind of perception or language understanding, so on. So AI can be divided in two parts, narrow AI and the general AI. Narrow AI meaning is that you can say some specific task we are designing the system. Then general AI, you can think when we talking about a system that can handle the generalized problems. That problems may be from one domain to other domain, not only the specific task or one domain. And then we can say that is a general AI based system. So like a lot of people are working on this AI based system design, either like either domain, either you can think in the communication, wireless communication community, you can think in the image processing community, you can think automobile industry, medical, healthcare, agriculture, everywhere people are working AI based system design. So what is the main motivation? Why people are going AI based design? Okay, so AI-based designs, definitely if you can see that AI is enabled in the Google and YouTube or so many platforms, so you will see that advantage of AI people are experiencing. So there is certain advantage why people are exploring AI, because it can optimize or system, or it can optimize the performance as compared to the conventional system design in certain applications currently. But people is still exploring AI for the complex system design. So that is a very hot topic of AI-based system design. It doesn't matter which field we are working. Even medicine and all these things, like even textile industries and the food industry, everyone is trying to use AI ML based system design, or like problem solving approach they are following. So general AI is still we are exploring. So we haven't achieved like till now some big outcome, but people are doing it. So AI ke further we can divide into the machine learning or deep learning based approach, so that we will going to soon see. So artificial intelligence can be, you can think, is a big umbrella. Then this artificial intelligence big umbrella AI and that AML and DL are setting. So further ML like DL is a sub part of the ML based approach. Okay, so these people just talking like people interchangeably nowadays, like artificial intelligence or MLDL approach. Okay, but you can think AI is a big umbrella. Okay, and these are the subparts of that AI. So AI has a lot of application, including autonomous vehicles, self-driving cars, personalized recommendation like Netflix, Amazon, uh, predictive analysis in business and healthcare, smart home device, AI-driven medical diagnosis, and drug discovery, etc. Then question is that what is the learning? Let me understand what is the learning aspect. In general, what is the learning meaning is that you have some kind of input. Okay, so input maybe I can write as a vector x. For example, input x has multi-dimensional element. Is a, maybe you can think a d-dimensional vector or m-dimensional vector. For example, if you applying for the credit card, then maybe your salary, your location, your occupation, or so many things you can think is a part of this input vector. Okay, and so this you can classify as an input. So you can think one application you can think as one input. So then you have a output. For example, many application in the exam. Then if your exam may be cleared or you can failed. Similarly, you can think credit card application. So many applications are coming. Then bank give them credit card or reject their application. So output you can think either select or reject, or maybe you have a good or bad customer you can identify. Sorry, this output y here not a vector, it is just element. Okay, so but it can be have a multiple decisions. So in that case, it can be output can have a vector. So you have an input x, then you have an output y. Okay, so what is our target? Based on the input x, we have to find out y. So we have to learn a function that can map the input vector x to the output y. So here I'm doing domain, this we can say codomain. So we have a function f that maps input to the output. So that is our target function, or we can say that learning function. Okay. So this target function is generally unknown to us. So we try to learn that function, how we will mimic this function, or how we are close to this function when we have the input and we have the some kind of output. Okay. So that way you can, I think that is a learning aspect. Okay. So this target function f is known. If this target function is given to us, then what we will do, just put the input in that function, then you have the output. So there is nothing to learn. Okay, but target function is unknown to us. Okay, so what we will do, we have a certain kind of data. So data, maybe you can think a input vector, then you have a output decision. So this one kind of learning you can think that people call supervised learning. So this is the input x1. So that is a multi-dimensional vector. Corresponding to this one, you have already output y1. For example, this is the customer's application in the bank. So you have a history of applications. So corresponding to each application, we have taken the decision in the past. So by one, you can say that is a decision of applicant one. Similarly, y2 you can say that decision of applicant two, so on. So you have n data points. So based on this data points, that is the historical data you have based on this historical data, we have to learn some kind of relation between output and input. Okay, so learning that relation, we use some kind of hypothesis. Okay, hypothesis may be like you can say that G is the hypothesis that map the input X to the output Y. Okay, that is some kind of formula based approach we can use. Maybe G hypothesis, you can understand it is a linear regression. Maybe you can say Y is equal to AX plus B kind of thing. or maybe you have some kind of neural network approach that maps input to the output. So hypothesis may be some kind of mathematical function, or you can have a neural network, or you can have support vector machine like that. So that way you can understand. So given the set of hypothesis, we will take this data. Okay, then we evaluate this hypothesis based on this data. Then what we will do based on this data points, we try to learn the hypothesis. Then we will find out this hypothesis G should be close to our target function F. Then we can say that we have learned the input output relation. Okay, so our aim is that we have to learn this hypothesis G, that is G is equal to F, or G is very close to F. Okay, so how we learn the G? That given the data points x1 up to xn. Okay, so that kind of learning you can think. So learning you can think, you have some kind of data. Based on the data, you are observe the data, then you can find out the relation between input and output. When new data is coming, or new customer, for example, is coming for credit card application, then based on the decisions of that you have took in the past, then you have some kind of like algorithm, or like input output relation. So you will evaluate that applicant's profile, then you can give credit or credit card to him or her, or you can deny that. So with that way you can understand. So this kind of we can learn that this, or we can say that this is some kind of learning. Okay, so that this learning can be especially machine learning part, it can be classified into multiple categories. So this is the reference of this figure. So machine learning can be classified in supervised learning, unsupervised learning, then semi-supervised learning, and then reinforcement learning. Further, this supervised learning can be classified into categories, regression and classification. So regression, we know that is when we continuously finding out the output, or continuously looking the output, or predicting the output, or estimating. For example, wireless communication, we are estimating the channel, so there's a regression problem. Then classifying you a certain number of classes or certain number of types you have in the output, then you're just separating out them. So that is the classification. For the wireless communication, you can understand like a modulation classification. For example, QPSK, so you have a 4 symbols, you are just quantifying or classifying, like this is the which constant, like given the input, this is going to the my constellation point. So that way you can understand that is a classification problem. So there are so many algorithms. Then further, this classification is divided by decision tree, random forest, artificial neural network, deep learning, Bayesian learning, support vector machine, and k-nearest neighbor approach. Similarly, unsupervised learning have other further type, that is the clustering, then dimensional reduction. Then you have a reinforcement learning and semi-supervised learning. So these are certain types of learning people are exploring, especially this supervised learning and semi-supervised, or this unsupervised learning people have explored a little bit more as compared to reinforcement learning. And people currently like focusing like especially in the wireless communication domain, this reinforcement learning, especially for resource optimization and the beamforming. So what is the supervised learning? Supervised learning, you have, maybe you people already know what is the supervised learning. So I'm not going to much detail. I'm just saying supervised learning, you have some data points. So data points means you have the input, then corresponding each input you have the output. So by looking at seen data, you can train the model, that is a generally neural network. So for example, this is the labeled data you have. This is tomato, carrot, or the capsicum. Then you train the model. Then you have a new data. Then you give. Then this model will give you that whether this is the carrot or tomato or the bell pepper, like that. Okay. So this is the supervised learning. So supervised learning means you have a input, then corresponding output you have. Then you try to learn the model. Then similarly, you have unsupervised learning. Unsupervised learning, we don't have like a labeled data, but you have some kind of like classification. Okay, for example, here you have the input, so you can you cannot say this is the elephant or camel, but you can say that this is one class, this is the another class, and this is the another class. So you try to differentiate the input based on the class, but you don't have exactly labeled data. But you can say based on this input, we have like these many output classes. So that is the supervised learning, and that you can understand the unsupervised learning. So you just classifying uh, uh, the output based on the some category, like category 1, category 2, or level 1, level 2, like that. So this is generally a approach we use in the supervised learning. So what we will do, you have a labeled observation. So you have the input, you can participate or divide the data into like two part. One is the training data, another one is the test data. So training data, you try to learn the model. Okay, then this trend model you can use to check the accuracy of this trend model based on this test data. So test data is not used in the training, but it is similar data for the training data. Okay, if it is different, then the neural network performance is not going to, or your neural network will not classify output properly. That we have generally seen. Then this is the semi-supervised learning. So semi-supervised learning, what is going on? You have some kind of labeled data, okay, that is used in the supervised learning, and some kind of unlabeled data that we use unsupervised learning. So that is a mixed data. Okay, so advantage is that it is between like supervised and semi unsupervised learning. So complexity you can reduce. Okay, having the good performance of the system. Okay, having the good performance meaning is that whether you are using the system for classification or regression, you can expect better output. Then this is the another kind of learning, that is a reinforcement learning. So reinforcement learning, what people do, you have a some agent do some action, okay, in the environment. Then what you will do, based on the action, you have some kind of reward. So based on that reward, that either you can give the reward positive or you can give the reward negative. Then the agent will take that action continuously. Then you monitor those cumulative reward, or then you will see that whether it is going to good or bad. That base we take the decision. So generally, one algorithm for reinforcement learning people are using, that is the Q-learning algorithm. So Q-learning algorithm, generally you have an agent. Okay, you have an environment. So you have particular state, then action. You have a set of actions. Then you do. Okay.
Full page নিতে পারছে না কেন?
Then you do some actions, and based on the action you have some kind of reward, and you have a new state. So you continuously do and learn. So agent is rewarded for good response and punished for the bad ones. So this generally we use for the supervised reinforcement learning. Then here I'm just summarizing like what are the differences among these learning models. So maybe have supervised learning, unsupervised learning, and then reinforcement learning. So we have already gone through what is the definition, what is the goal. So we can use predict, or classification, or regression model. Okay, and then we generally use these algorithms like linear regression, decision support vector machine, all these things. Okay, that we are highlighted here in this figure. So there is nothing new, but that is the summary. Okay, but we have a certain advantage of supervised learning, like accurately prediction, easy to evaluate performance, and this, for example, reinforcement learning learns from the sequential decision making, adapts a dynamic environment. That is advantage, but it has high complexity. So you have a certain advantage, but you have certain challenge also associated with them. Then you have a artificial neural network. So artificial neural network, if you see that it has certain kind of input layers, then have hidden layers and the output layers. Then this neural network in structure is inspired by the human brains. So what we will do, we will try to mimic the human brain through the artificial neurons. Okay, so neurons are interconnected to each layer. Then what we will do, we have like certain kind of learning on those neural networks. That is the input layer and the hidden layers and the output layers. So we have a forward propagation, activation function, backward propagation, and loss function all are associated with artificial neural network. So you people know it, so I'm not going to much detail. Okay, then neural network can be classified in different networks based on the network structure, maybe feed forward neural network, convolutional neural network that generally we call CNN, then recurrent neural network RNN or autoencoders or the GAN. So that is a general adversarial networks. Okay, so these are different network stacks that people are exploring for like doing some classification or regression task or designing the AI-based systems. So this is the like a structure of neural network. You can understand the input. So here you have input layers. Then these are the interconnection between the nodes. So that is the hidden layers. And then the output. Then you can see each neuron, you have some kind of activation function so that the output, this has, for example, this one multiple inputs are coming. So these inputs have certain weight. Okay, weight means so these are multiplied. That is a W vector. Okay, W1, W2 up to Wn, where you have n layers, n nodes. Then X is the input. So you can see that this is the weighted input. Okay, so each input is multiplied by particular weight, so that you can say that is a Wx. Then you have some kind of Ysing, that is the that we say the B. Okay, so that Ysing generally create like a data shifting, maybe like positive or negative, you can understand. So that is the weighted summation of all the inputs. Okay, and then what kind of function in this node will do? It will use certain non-linear activation function. So that is called activation function. So that function can be classified using the F. So each output you can write as F Wx plus B. Okay, so this is the output of this node here, for example, and that is a weighted summation of all the inputs that is coming from all the previous nodes. Okay, so that way you can understand. So this so learning meaning is that we have to learn what is this weight and Ys parameter of these nodes. Okay, so you have a multiple layers, you have each layer have multiple nodes. Okay, so you have to learn this weight and Ys for all the nodes and all the layers. Okay, so this is generally we classify or we can write using the like a big vector. Okay, so that vector can have like a multiple bits and multiple bytes elements. Okay, so this vector we have to learn given the data. Okay, so we can say that we are learning, the neural network is learning, meaning is that we are trying to finding out the what is the optimal bits and what is the optimal bias for the given data points. Okay, so for example, this is the neural network architecture. So you have the input here, you have the output here. So given the data set, what you will do, you will just give the data input data to this neural network here, and you will observe the output here. Okay, then you advance, you know the output, so you try to minimize the loss between actual output and then estimated output. Then by minimizing the loss, what you will do, you just try to adjust these weight and Ys parameters. Okay, when your loss is going to minimum, meaning is that actual output and estimated output, that is, or output of the neural network, that they are very close. So meaning is that these weights are optimized. Okay, so for given the data, these weights are optimized, so that we can say that neural network is trained or neural network has learned. Now I'm going to move the wireless communication. Okay, so wireless communication, if you understand that, meaning is that where we have a data generally we are writing in forms of bits. Currently we are using like a bit binary data representation, 0 or 1. Then what we will do, this data, this binary bits we are transmitting, that is generally carryable data. So that data we are transmitting through the wireless channel from one point to another point, or that we call from transmitter to receiver. Okay, or we can say base station to mobile station. Okay, or mobile phone, that way you can say. So transmitting the data from one node to another node through the wireless link, that that is generally called wireless communication. It is unlike the wired communication. Wired communication, we have a like a dedicated wire between the two nodes. But wireless, we have electromagnetic waves that are freely propagating in the environment. Okay, this wireless communication is different from the wired communication because you can see there is no dedicated path between input and output, or you can think between the two nodes. So some challenges are associated in the wireless communication. Challenges are associated, like you can understand, that is the first impact is the fading. Okay, because you can see that fading, maybe you know that the fading generally you can say that is a fluctuation in the received signal strength. Okay, so this fading is associated in the wireless communication. Then another thing is that noise is also associated. That is hardware components make certain noise when you designing the system. So receiver, when you're talking about the receiver or transmitter, certain kind of noise is associated. Then you can see that multiple transmitter and receivers are operating in the environment. So interference is also associated. Okay, so that is the fading, interference, and then the noise. So these are very critical parameters that will decide the wireless communication performance. Okay, so wireless communication can be classified in many categories. One, you can have radio communication like AM or FM radio station, walkie-talkie, and broadcasting systems, for example, television. Satellite communication, that is a GPS, a television broadcasting, weather monitoring. You have a Wi-Fi, that is a routers. Cellular network, generally we talk about mobile phones. So that is from 1G to 5G we have reached, and we just moving on the 6G wireless network design. Then we have a Bluetooth, that is generally, or the Zigbee you can have, or the UWB you can have for the short range communication to connecting the devices or connecting the IoTs. Okay, IoT devices you can think. Then we have a infrared communication. So that is a short range communication again. For example, the remote controls or sensor connections. Then visible light communication, that is also there for short range communication. So you can see that wireless communication can be categorized into different categories, maybe short range communication, maybe long range communication, maybe connecting the for example, satellite communication, so non-terrestrial networks or terrestrial networks. So different applications you can see. So wireless communication is evolving very fast. That's why we are gone through all the evaluation from 1G to 5G, and we are going very shortly in the next 4 or 5 years to the 6G wireless communication. So the reason is that if you see the application or see our activities in the daily life, okay, so we have a different applications, we have a different motives every day. If you think our mindset or the society's living styles or industries demands, we need certain connection among the nodes. Okay, so like a huge connection demands is coming from the various applications. So you have a different devices, we have to connect them through the wireless link. So obviously wireless links have more flexibility as compared to wired. Okay, so that is the main advantage. Okay, and so this connecting all the devices together, okay, is a big challenge. Okay, so large number of connections we have to support. We have a wireless network that can support large number of devices. Then definitely we have a data rate requirement. So different applications need different data rate requirement. So we have to go high data rate, certain application we can have a low data rate or moderate data rate. So these diverse applications of the wireless communication are focusing us to design the next generation wireless network so that we can fulfill the demands from the various sectors, either healthcare or the agriculture or the industry or the cellular network point of view, if we can talk. So these are our motivation to explore the wireless communication or focus on the design of next generation wireless networks. So this is the evaluation of evolution of wireless network. If we see that from 1G, that is 90s 80s. Then so this is generally analog in nature. Then we have a 1990, we have a 2G GSM, so that is based on the TDMA FDMA. This is the first digital mobile phones. Then 3G, that is basically that is a CDMA technology, code division multiple access. Okay. Then we have a 4G that is based on this OFDM, orthogonal frequency division multiple access. Then it started deployment in 2010. Then we have a 5G, so that is started 2020, and that is again based on the OFDM technology. So this is 5G generally focusing on the IoT applications. Then 6G that we expecting on 2030 deployment. So that is some enhanced features over the 5G. So you can see that as time progressing, every 10 years we have a new wireless technology that we calling 1G, 2G, 5G like that. So every generation networks have a different capabilities. Okay, these capabilities, if you can see that 5G network, so that is very flexible as compared to 4G or 3G, and it also have the backward compatibility support. Okay, then it is have high data rates. It can support diverse applications as compared to the previous generation. So that kind of application we are exploring, or that kind of design we are exploring when we're talking about the next generation wireless networks. So our main motive is that why we are so what is the happening when we are talking about the next generation wireless networks. So as I pointed out, we have certain issues in the wireless network. Issues maybe you can think about, and I'm just focusing on the key components. You can think you can have interference, you have a resource allocation policy, how to optimally allocate the resource, or you have a spectral efficiency point of view. Okay, and then you have a energy efficiency. Energy efficiency is very critical if we think in the current wireless technology or the coming wireless technology. Why we are focusing on the energy efficiency? Energy efficiency, like given the energy, how much data or bits or data you can transmit from one node to another node, that you can say that is the energy efficiency. So like you minimize the energy for transmitting for transmission from data for data from one node to another node, that you can say energy efficiency. So we are minimizing the energy efficiency. If you can think like your charger, maybe assuming 5 or 510 volt charger. Okay, but if you can think like this power at the power plant, when power is generating and then is distributed to our homes or offices, so that is like a huge loss in the distribution. So this 5 watt may be like 50 or 100 watt at that your uh, generation point generation or generating point. Okay, so power efficiency is very important parameter currently in the wireless technology. And another thing is that if you can see that billions devices are deploying wireless, billions device currently, you can see so many devices. Okay, then in the future these devices number will again increase like anything. Okay, so even if you can think, if you will consume, each device will consume 2-3 baht. Okay, then you can think how much power we can go in to consume. Okay, so that way you can think. So everyday aspect I'm talking, so you can think that how much power we will for power we need to support these devices. So we can have a green devices that can maybe self-sustainable. Okay, that consume very less power. They can like self recharge rechargeable for through the solar energy, or maybe you can say some that electromagnetic waves, generally people calling that as a swift. Okay, so that energy efficiency is another aspect we are talking. Another aspect we are talking about the spectral efficiency. So spectral efficiency meaning is that spectral efficiency we mean talk means we are talking about the frequency bands that is generally used for data transmission. So if you can see that uh, more and more devices are coming into the network. Okay, means more and more devices are connected through the wirelessly. So we have to support large number of devices. Okay, so given the bandwidth, for example, if you give me 1 megahertz bandwidth, I can support maybe 50 device, and if you want to connect 200 device, then you need more bandwidth. Okay, so that way you can understand the spectral efficiency. So for spectral efficiency, we have to have like given the bandwidth, we have to connect more devices, or we can transfer more data. That way you can say the spectral efficiency. So for connecting the large number of devices, we are also exploring the high frequency band. Generally, we are sub 6 gigahertz band to are going to the like above 10 gigahertz. For example, 5G phones, we have a like a band above 20 gigahertz. Okay, that is a reserve. Okay, unlike the 4G or like 3G mobile phones. So we are moving toward the high frequency bands. Okay, so we are talking about high spectral efficiency. We are going to the high frequency bands. We are talking about the energy efficiency, and we are talking about the data rate. Okay, we are talking some other parameter also we will see. So these parameters focusing over the design of that system or the network, we should think differently, not like the previous generations. So that's why people are thinking differently. They are coming with different solutions, and those solutions can like help us to accommodate the demands that is coming from the various sectors, so that we can have a next generation wireless networks. That way we can think. For example, if you look the IMT 2030, that is a vision for the 6G mobile phones. So if you can see that this immersive communication and that massive communication, hyper reliable and low latency, this is the extended version of the 5G networks. So this capability is going to enhance in the 6G, that we calling at immersive communication, that is the EMBB node. Then MTC is going to massive communication, and then URLC we are calling H, hyper reliable and low latency communication. Then apart from these extended version of the three's capability, we have a three new features, that is the integrated sensing and communication, ubiquitous connectivity, and then integrated all and yeah, integrated AI and communication. So these are the three extra points are added in for the 6C wireless network design. Okay, so let's understand one by one what these points, what we are talking about. Okay. So these capabilities going, existing capability of 5G network is going to enhance, but these three activities are going to add it for the 6G networks. So integrated AI meaning is that AI based wireless system design people are talking. AI meaning is that we can use the AI either doing the like some receiver design, transmitter design, or the resource optimization at the both uh, transmitter as well as the receiver, so that we are saying AI based decision making capability in the system should have. Okay. Then we have a integrated sensing and communication. So its meaning is that currently what we are doing, we have a radar system and we have a communication system. Okay. So radar system and communication system generally separately designed. Okay. You can have a radar system. They have generally different operating frequency. Communication system designed differently, so they have a different frequency range. All the hardware and the frequency spectrums are different. Okay, so now what people are talking like function, if basic functionality, if you can look the radar and communication, they are very similar. Okay, we are doing estimation. Okay, then detection. Okay. So people thinking like why we should design like a radar system differently and communication system differently. Can we design a single system that can support both sensing capability or communication capability? Okay, so that same system will work as a radar and communication system, so that is calling integrated sensing and communication. So that way we can achieve more spectral efficient wireless network design, and we can have more capability sensing and communication, meaning that we can enhance the system performance. So sensing will help us optimizing the resources meaning is that either bandwidth you can talk, power you can talk, or the computation power you can talk. Okay, so integrated sensing and communication system are more efficient and cost of point of view, okay, and the resource point of view. So all the aspects can be optimized if we can have this kind of capability. Then ubiquitous connectivity meaning is that certain like rural and urban areas, maybe some parts are not connected, so you have to connect each and every place. Then that we have like a terrestrial and non-terrestrial connectivity, so unified connectivity we are looking. So it doesn't matter either you on the earth or you in the like air, so you will get the everywhere internet connectivity, and even in the flights everywhere. So that is meaning people are talking. So integrated terrestrial and non-terrestrial network design. So that is again a challenging issue. This is a challenge. This is not a trivial task because you have a different parameters when you designing the wireless system for the satellite link, and when you designing the wireless system for the one node to another node on the earth, then you have a different issues. Then integrating them and designing jointly system. So we have some non-trivial problem, non-trivial task that we have to solve before going to that capability. So these are have advantage, then we have a certain task or certain challenge that we need to fulfill. Okay. Then this new capability is IMT 2030 added. So these are the coverage. We have a sensing related capabilities, AI related capability, all these things, and these are the existing KPIs. Further, these KPIs are enhanced. For example, this is the KPI for 5G, and then these are extended for 6G wireless networks. For example, if you're looking at the density, so 5G we are looking 10 to the power 6 per connection per square kilometer, or devices per square kilometer, but we are looking like 10 to the power 6 to 10 to the power 8. So 100 times we are increasing the density of the devices in the same area. So that way you can think. So these are the enhanced capability of the 5G network, and these are the new features we are going to add in the 6G. So that is the people thought. It is not finalized yet, but people have some like a thought in their mind like how 6G will network help us to solve these challenges that we are facing currently in the 5G network. So now, as I pointed out, like we are going to move in the OFDM system. So OFDM system, you can orthogonal frequency division multiplexing. This is very versatile technology or generalized technology we are using in 4G and 5G cellular networks, Wi-Fi standards, digital broadcasting, IoT and low power networks. It has certain advantage. That's why people are using the OFDM. For example, spectral efficiency. So if it has high spectral efficiency, because if you can see that OFDM subcarriers, they are like they are overlapping, but still they have like orthogonally behave. Okay, so we have high spectral efficiency. We have a robustness. Robustness meaning is that when you have a flat fading, okay, and frequency selective fading. When you have a high channel bandwidth, that time we feel the frequency selective channel. So with the help of OFDM technology, we can convert this frequency selective channel to the flat fading channel, where each subcarrier like independently faded. So we can think we have a robust fading, a robust system against the fading. Then low complexity. Low complexity meaning is that OFDM is very simple system. You can think very simple, meaning that OFDM transmitter has just IFFT operation, inverse fast Fourier transform, and the OFDM receiver generally has the FFT operation. So this is very simple. Then scalability, so that like a bandwidth or that spacing among the subcarriers we can adjust like in the 5G and R. So there is a flexibility also there, scalability is also there. So there is certain advantage of the OFDM. That's why people are pursuing it in the 4G, then continuously in the 5G, and 6G maybe, or even like people thinking like maybe 60-70% the chance that OFDM will go in the 6G also. So like, do you have any query up to here? Then we go ahead. Hello? Hello? Hello, can you hear me?
Hello, sir. Tell me, sir.
No query,
Yes,
sir.
sir.
Please continue.
Okay, okay. So now I'm going to discuss what is the OFDM. Okay. So as we remember the CDMA, code division multiple access technology. So when we have a GSM, that time we were talking about the high data rate. So people like think like how to support the high data rate. So people suggest we can have a high bandwidth. Okay, so through the high bandwidth we can support high data rate. Then what people did, they designed the waveform that can high bandwidth and then have a lower time duration, because bandwidth and time are inversely proportional to each other. Then CDMA, if you remember that, you just a modulator, then you have a spreading. Okay, so spreading sequence, so that increase the frequency of transmitted signal. But problem is that CDMA technology is that that receiver design is very complex. Okay. Then as further we go for high data rate, then this equalization problem is very challenging in the CDMA technology. So CDMA technology is designed by considering that channel, that is the wireless channel we have between transmitter and receiver, by considering the wireless channel in the time domain. Okay, so let's understand what do you mean by time domain and frequency domain view. For example, this is the wireless system. So wireless system, we have a transmitter that generally source and the modulator. Okay, then you have equalizer, demodulator, all these things in the receiver side, and this is the wireless channel. So our thought is that we can design the transmitter, we can design the receiver, we cannot do anything in a wireless channel. It is like environment dependent. What are the surrounding area we have? Okay, so wireless channel will behave according to that. For example, if you have a rural area, you have urban area, then channel behavior will be different. So we cannot do anything with the wireless channel. Okay, that completely depend on the surroundings, but we can do the design change at the transmitter and receiver. Okay, so then this high data rate, that is a problem is coming due to this high data rate, that is the equalization in the CDMA. Then this OFDM design came into the picture. So what people think, you can think wireless channel in the frequency domain. It is the same channel, but you think or you can perceive that wireless channel in the frequency domain. You write that channel into the frequency domain, then you try to design the transmitter and receiver. That is the criteria. Okay, CDMA, what people were doing, they think wireless channel in the time domain, then they were designing the transmitter receiver by considering the time domain approach. So coupling between transmitter and wireless channel in the OFDMA is going to happen in the frequency domain. Okay, but CDMA, it was in time domain. Okay, so problem is coming the equalization in the CDMA when you go into high data rate. So we have like a delay spread. Okay, delay spreading meaning is that when you sending this a simple impulse, but due to the multiple paths, okay, we are receiving the multiple copies of that same pulse. So you can see this is a non-zero interval, only this is small portion that is located on zero. But due to the multiple paths, we are getting signal from here to here. Okay, that is called delay spread, tau max. So this delay spread will create the problem. Okay, in the high data rate application. Why it is create? Because we have a high data rate, meaning is that we are transmitting very short time duration pulses. When time duration of pulse is very short, then this delay spread will be more. Okay, that overlapping between two symbols, consecutive symbols, you can think is more. So when we have a more overlapping between the two consecutive symbols, then separate out them at the receiver to decode the data is very challenging. Okay, so OFDM, what they think, they break down that frequency band into the smaller bands. So what they think, like a wave time duration of pulse increase in the time domain, so like a small overlapping we can adjust. So OFDM is basically designed to considering the delay spread of the wireless channel to overcome the delay spreading problem of the existing CDMA systems. Okay, so that way you can understand. So delay spread you can understand this way. You have a transmitter, you have the receiver. So transmitter, that is the line of sight path, LOS path, that is directly coming. And then you have a reflected path that is coming from this building, that is a reflected path. So you can see that non-line of sight path. So delay of this path is tau 1, that is R1 upon C, that is our distance divided by speed of light. Then you have a reflected path, that is the tau 2, that is total distance R2 plus R3 divided by C. So this tau 2 is generally higher than the tau 1. Then delay spread you can characterize it as like a last path minus first path kind of thing. So tau 2 minus tau 1. So you have a multiple paths, then this delay spread further will increase. So overcome this delay spread problem, OFDM system is designed so that we can have a simple equalizer. So this is the block diagram of OFDM. Mostly people know what is the OFDM, so I'm not going too much detail. So you have a transmitter, then you have a modulated data symbols, then you have a serial to parallel, then you convert this. This is the frequency domain. Okay, these data symbols you can understand in the frequency domain. And then you have a AICTE, so that will convert frequency domain signal to the time domain signal. Okay, then you have a parallel to serial. Okay, then again you have a cyclic prefix that generally take care of this and this delay spread, and that is inter-symbol interference. Okay, then you have a transmitted signal, then you will receive the signal that then you remove the cyclic prefix. Okay, then again you convert serial to parallel, then we remember that data in the frequency domain, so we have to decode data again in the frequency domain itself. So we convert this time domain data to frequency domain by using the FFT operation. Then we have a demodulator. Okay, and then the demodulator is very simple because it's a single tap equalizer, means the kth subcarrier received signal is divided by just kth subcarrier channel. That's it. So that is a single tap equalizer. So that's why OFDM system is very simple, and IFFT and FFT operation are divided between transmitter and receiver. So this I'm just leaving. This is the PAPR issue. So this is the like a dummy kind of recording we are using. So I'm just leaving it. Then this 5G also use this OFDM is also used in the 5G communication scenario. So, but what we are doing in this 5G, we have a massive MIMO beam management capability. Okay, so this wide range of carrier frequencies, we can have like a large number of carriers, and then each carrier frequency is higher than the like a 4G or LTE mobile phones. Then we have a various deployment options like a large to small coverage area per base station, diverse use cases, maybe human centric or machine centric. So we can have certain flexibilities there in the 5G NR that is really based on the OFDM technology. So this some disadvantage of OFDM is the high PAPR, peak to average power ratio. Okay. This is happening due to the multiple subcarriers, because you can think what is the meaning of PAPR, like peak to average power ratio. So in OFDM, as I pointed out, whole frequency is divided into multiple frequencies. Then these multiple frequencies are called subcarriers. Then each subcarrier is independently modulated, meaning is that first carrier you can put some data, then second carrier I can put data, third carrier someone else can put the data. Okay, so independently modulating. So when what will happen when all the subcarriers will add together, then maybe data added constructively or destructively. So you will observe in the transmitted signal some peaks and some valleys. Okay, so that peak to valleys or that is the average value of the transmitted signal, that ratio is very high. That is called high, and that is a PAPR, peak to average power ratio. So that is high in the OFDM, but that is a problematic. Why it is problematic? Because when you have a high PAPR, that time we cannot have like a high efficiency or high efficient or the efficient power amplifier at the transmitter site. Yeah, okay, because a power efficient amplifier, if you have, we have to have like a high linear range of that power amplifier. So that is not possible when you have a high PAPR. Okay, so that is a drawback. Like like when you have a high PAPR, that time you are losing the efficiency of that power amplifier that is sitting in the front of RF front end. Okay, so these are the certain challenge, but these like a PAPR is not an issue that people have tackled it. Okay, so but that is not main issue. Then main issue is coming here, the performance degradation when comes to high mobility scenario. Okay, as I pointed out that CDMA system is designed by considering the wireless channel in the time domain view. Then OFDM system is designed by considering the channel frequency view. Okay, so OFDM is basically designed to help or overcome the delay spread effect, that is inter-symbol interference. Okay, but if you can see high mobility scenarios, Doppler is also associated. Okay, that time people didn't realize this high mobility scenario application of OFDM. They haven't thought about like how to handle this Doppler effect. Okay, that is the high mobility communication scenarios. So that is the problem in the OFDM system. Current OFDM system, if you are using the conventional OFDM system, you cannot have high Doppler effect in that system. System cannot like handle that high Doppler. So your performance is going to degrade in high mobility scenarios. Okay. So this OFDM, you can again think this is the like a total bandwidth of the system, then is divided into the smaller bands, then each smaller bands independently modulating, then you're transmitting. So you can see some waveforms are added consecutive. So this is the frequency domain view, but if you can see think in the time domain, so you have first symbol, then the guard interval, then second symbol, then guard interval, and so on. Okay, so you people know it, so I'm not going to this too much details, but I'm just highlighting that OFDM shortcoming or that drawback is that it cannot suitable for high mobility scenarios because that is a Doppler effect. So why this Doppler effect is associated with the channel. Okay, so as I pointed out, wireless channel has two physical parameters. One is the delay spread. Okay, another one is the Doppler spread. Okay, so Doppler spread I already pointed out due to the multiple paths. You have the different arrival time of the signals. Then you have the Doppler delay spread. This Doppler spread is coming when you have a movability in the system. For example, this is the transmitter. This is the building. Then you have a high-speed car that is moving. So when signal is coming to this receiver, then you will see that this is the direct path and the reflected path. So you will experience the Doppler in the received signal because this velocity of this car is changing. Okay. So what will happen, this Doppler frequency we characterize the line of sight path is the new. This is a new one, that is the FC, the carrier frequency, and V is the velocity of this car. And then angle theta is 0. So you can think this is the 1, cos theta is equal to 1. So that is the speed of light. So Doppler is Doppler of this line of sight path is can be given as FC V upon C. So you can clearly see that if carrier frequency is increasing, Doppler is also increasing, and this velocity is increasing, then Doppler will also increase. Okay. Then similarly, you have a reflected path. Then reflected path and Doppler you can categorize using again this one, angle is theta. So Doppler spread similarly characterized like nu 2 minus nu 1. So that is called Doppler spread. Okay. So now you can understand that channel can have two things, that is a delay spread and the Doppler spread. Okay. These are the two physical parameters. So number of reflectors are there. Then based on that you have a delay spread and Doppler spread. Then the received signal, for example, this case, this is the received signal by considering these two paths. So this is the H1 that you can say that fading coefficient or channel coefficient of line of sight path. Then e power j2 pi mu 1 t minus tau 1. Okay. Sorry, this is the new one, not the mu, new one. So this is the Doppler of that path, and then t minus tau. So this is a delay. Okay, so delay. So this part, this is related with that fading. Then you have a Doppler, then you have a delay. And this is the transmitted signal, so this is a delayed. Similarly, you have another path, so you have a delay and Doppler. So you can see that received signal has both delay and the Doppler. Okay, when this car is not moving, you have a stationary mobile, then you can say that Doppler is 0, so this term is going to 1. Okay, so you can think that generally we have both delay and the Doppler. Okay, then I also highlight this Doppler will increase as carrier frequency will increase or speed of vehicle will increase. So as we seen that we are going to 5G communication or 6G communication, like we are going to about 20 gigahertz bandwidth. So if you consider 2 gigahertz signal for the the 3G mobile phones or in the 4G and at 20 gigahertz, then the Doppler will be very like different. Okay, so you cannot you can experience very high Doppler and the same speed if you are using a band about 20 gigahertz, and you can have very smaller Doppler when you have like 2 gigahertz carrier frequency. So that way we can understand when frequency bands like we are going to high frequency bands. So that's a Doppler phenomena is again going to the severe and then that is also related with the velocity. So if velocity like high speed communication, if you're talking about like a bullet trains, so velocity is very high. So this Doppler we cannot neglect. Okay, so such scenarios, current OFDM technology performance is not good. Okay, that is the as I said, OFDM is just designed by considering the delay spread. People don't think about, like, didn't think that time what is the Doppler impact on those systems. So this is the wireless channel. Also, I'm just generalizing this wireless channel in different domains. Okay, so here you have a wireless channel, that is a channel H, time and frequency. So this is called time frequency channel that is generally used in the OFDM system. As I pointed out, OFDM looks the channel in frequency domain. Then you have the delay and Doppler channel. So this delay is tau and Doppler is nu. So you can go from time frequency channel to the delay Doppler channel by using the SFT or ISFT. Okay, symplectic finite Fourier transform or inverse symplectic finite Fourier transform. Then you can also go from delay Doppler channel to the time variant channel, that is the delay time channel. Okay, or time delay channel. Okay, and then you can have like a frequency Doppler channel. So frequency Doppler channel, you can think BF comma nu. So nu is the same. So if you take the Fourier transform with respect to tau, then you have a frequency. Okay, so we have a same wireless channel, but we can represent in the different domain. Okay, so that is the idea, like same channel is represented in the different domain, then view, or that if you plot the channel in the different domain, then you can see the channel behavior differently. Okay, if you plot the channel in the frequency domain, if you plot the channel in the delay Doppler domain, you will see the channel differently. Okay, so that's why people thinking why we cannot design the system in delay Doppler domain. Okay, because delay and Doppler 2 are fundamental aspects of the wireless channel. Okay, so people think, can we design the wireless system by considering channel as a delay Doppler domain? Okay, so that people are calling that OTFS system, orthogonal time frequency space modulation communication network. Okay, so let's understand this is the OFDM. So as I pointed out, Doppler is proportional to the velocity and carrier frequency. Then what will happen when we have a high Doppler? Then this is the OFDM grid. Okay, you can think OFDM system. You have a time and frequency. So these are the subcarriers and these are the slots. So you can first time slot, second time slot, or you can say symbols. Okay, and then here we have a data. Okay, so what will happen when we have a high Doppler? That time intercarrier interference will arise. Okay, what do you mean intercarrier interference? Meaning is that this data point will create interference to this data point. Okay, or this can create interference to this data point. Okay, so this kind of interference is coming that will limit the performance of OFDM system. So that's why OFDM system is not suitable for like a high Doppler communication scenarios. Okay. So how OFDM will handle this OTFS will handle those challenge that is coming in the OFDM system. So OTFS thinks channel in the delay Doppler domain. So we put the data in the delay Doppler domain instead of time frequency domain. So this is the 2D view of the OFDM. So OFDM, we are putting data in the time frequency domain. This is the OTFS modulation. So this is the two-dimensional modulation scheme. So we are putting the data into the delay and Doppler domain. Okay, so we have a delays and we have a Doppler. Okay, time inverse is Doppler and the frequency inverse is delay. You can say that. Okay, so we're putting the data into the delay Doppler domain. Okay, but delay Doppler domain is not a real domain. So you can say that we have to convert back a delay Doppler domain to the time and frequency domain. So we'll see shortly how we'll do that. Okay, so that is the idea in the OTFS system. So fundamental idea in the OTFS system is that we can put the data in the delay Doppler domain instead of time frequency domain, like in OFDM. Then putting the data in the delay Doppler domain, we can have a different wireless system, okay, that can have better capability as compared to the existing systems. So let's understand relation between them. So when OTFS is proposed by Hadani, okay, so what we thinking like we have to have some kind of compatibility between the two system, OFDM system and OTFS system. Okay, so they design this one like you put the data in the delay Doppler domain. Okay, then this delay Doppler domain you can convert into the time frequency domain. So that is a 2D OTFS waveform. So this delay Doppler domain is converted to time frequency. Now this is your OFDM system, current OFDM system. Okay. Then you have a time frequency domain channel. Then this the receiver side, you have a time frequency received signal. Okay. So this is the OFDM system, this one. Okay. Then this is the new system that we're calling the OTFS. So you can see that OTFS is very similar to OFDM. Somehow we do this one conversion at the transmitter side that will convert delay Doppler to time frequency. So this extra conversion is required at the transmitter side. And this extra conversion is required at the receiver side that will convert time frequency signal to the delay Doppler domain signal again. Okay, why we are again converting? Because we are putting the data in the delay Doppler domain. So we have to do the detection of the data in the delay Doppler domain again. Okay, so this extra blocks, that one block at the transmitter side and another block at the receiver side is sitting. So we have OTFS system can have compatibility with the OFDM. Okay. But if you want to understand the OTFS system independently, you forget about the OFDM, then you have to think that you put the data in the delay Doppler domain, understand the channel in the delay Doppler domain, then you have a received signal, then you just design the system independently. You don't go from here to here, then here. Okay, OTFS we convert frequency into the time and so on. Okay, so you have think, put the data here, then receive the data here, and think in the delay Doppler domain everything. Okay. So that maybe you can optimize the system performance. Okay. So this people generally recently calling that is the like one step OTFS system, and this two step people calling it because two step is this version going from delay Doppler to time frequency, then time frequency to time. That is the IFFT operation we do, and the here FFT operation we do. Okay, so here to here that is a single step people are talking, and if you go through the OFDM that people call it two-step OTFS system. So two-step OTFS system has back compatibility that is with the OFDM system, and single step OTFS system independently designed without considering the OFDM system. So this is the block diagram. If you can see the OTF system, I'm just going high level view of the system design. I'm not going to too much detail inside the box. So you have a data that is a two-dimensional data, as I pointed out here. OTFS is a two-dimensional modulation scheme. Okay, you have to think 2D. So you have the data that is a K comma L, that is a delay index and Doppler index, you can think. So data in the delay Doppler domain, you modulated data. Then this delay Doppler domain we have to convert in the time frequency domain. Okay, so that we have some kind of converter that is called ISFFT, inverse symplectic finite Fourier transform. So this ISFFT is nothing but the pair of FFT and IFFT. You have a rows, you have the columns. So you have to take the IFFT row wise, then the column wise FFT like that. So this way you can think this is the like a matrix. So row wise operation and then column wise operation we are doing. Then delay Doppler is converted to time frequency domain. Then time frequency data is converted to the time domain. That is the Heisenberg transform. Okay. Then you have a channel in the delay Doppler domain, h tau comma nu. Then you have a received signal again in the time domain. This time domain signal is converted to the frequency domain, that you can Wegener transform. Okay. So if you have just single symbol, then you can think FFT operation. Okay. Then this delay, this time frequency signal is converted to the delay Doppler domain. Okay. So you can think this this is the OTFS modulator that has two blocks, ISFFT and the Heisenberg transform. Then OTFS demodulator, you have again two blocks, that is a Wegener transform and then SFFT. Okay. But if you just think this one, this three block, that is the OFDM system. Okay. And these two extra blocks are coming in the OTFS system. So you can think like a post-processing block and pre-processing blocks in the existing OFDM system. So OTFS system complexity is not too much high as compared to OFDM, except these two extra blocks. Okay, and some like detection performance definitely by KL. You have a received signal. Now we have to decode the data. So decoding complexity is high as compared to the OFDM. So this is the idea, like how OTFS system works using the OFDM model. Okay, so this is the backward compatibility of OTFS system. Then let's go to the little bit about like how we can use the ML or DL in the wireless communication. Okay, so like we have two streams, wireless communication, you have a machine learning. So machine learning independently people have explored maybe in different applications, image processing, speech, or resource optimization in certain applications. Wireless communication is independently designed. So wireless is a model-based approach. You have some transmitter, you have a wireless channel, you have a receiver. So like you do these steps in the like certain fixed steps are there. So you have a model-based approach. Okay. So you have a certain strength because wireless communication people are studying from like a long time, like 50, 60 years or more. Okay. So that knowledge you have, okay, so that knowledge can you take into the machine learning algorithms. Okay, machine learning approach generally, if you see that they considering the things as a black box. Okay, so that machine learning strength and the wireless communication strength, that is a model based approach. Whatever the belief or whatever the prior information we have about the wireless system, those prior information you can put into the machine learning model while we designing the system. So that is the idea of MLDL based wireless communication system design. So you can have certain better system in terms of spectrum spectrum sensing. So like a beam forming and beam management, if you can take the help of AI ML in the communication system. Then people exploring this AI ML for channel estimation, interference management, modulation detection. Modulation detection means like classification problem, you can think. So these are the different application of AI ML in the wireless communication. So people are using resource allocation, traffic prediction, security, and then eliminate interference, save energy for designing the energy efficient system, channel state information. Okay, so there are different application people are exploring. Okay, so that depend on the like someone's requirement, what kind of application of AI ML you are looking. Okay. Sometimes you can jointly explore all the possibilities of AI ML in the wireless communication system design. Sometimes you can like use the AI ML for resource allocation, or sometimes you can use for like a channel estimation. Okay. Okay. So as my point of view, if you can think AI ML in the wireless system, so resource optimization is one thing that people are exploring, and I think it also gives better performance. Another thing is the interference scenario. Okay, so wireless communication, what we will do, we generally design the maximum likelihood decoding algorithms. Okay, so maximum likelihood decoding, you have to have certain kind of model. Okay, model meaning is that you have a certain kind of equation. Okay, those equation you explore, okay, or to decode the data or transmit the data. So interference scenario, certain interference scenario, for example, like in-band interference or out-band interference, like a single cell or multiple cell scenario, multi-user communication scenario. Sometimes interference equation you cannot model exactly. You can have like some rough estimate of the interference. So certain scenarios, interference limiting scenarios, you can use the AI ML to have better performance. Okay. So and then another one is the like a complexity issue. Okay, AI ML, with the help of AI ML, we can reduce the system complexity. System complexity meaning is that when you're doing the maximum likelihood detection, so certain applications you have to looking so much like classes, so many channel states, so many things. Okay, so the complexity is very high. Okay, but if you can use the AI ML, you can reduce that complexity. So when you don't have exact model, that time you can explore the AI ML for better performance. You can explore the AI ML to reduce the system complexity because you can manage the resource more effective manner as compared to maximum likelihood detection with having the like almost very good performance. Okay, and then you can have some resource management or like a resource prediction. Okay, so that scenario people are exploring, and then that scenario may be like a very good in the wireless communication. Uh, um, So this is the like how people deploy this AI ML model in the wireless communication. So you have some neural network, you have some data, then you have some output data. So you have trained that model. Then this trend model, you can have some new signal that is the calling the test data. Then based on the new signal, try to find out what is the output. Okay. Then this error between actual and then output and then estimated output, you can say that loss. Okay, so that performance you can evaluate. So that is a training is done based using certain data. Okay, that is a maybe supervised learning or supervised learning. And currently people are also using the reinforcement learning, for example beamforming optimization. So what people doing, you have some kind of feedback in the system from the like uplink scenarios. You have a kind of channel state, then channel state is predicting by the neural network, then channel, then you're doing the beamforming. Okay, so as new data is coming, so like this beam forming vector is continuously like evolving. So this is kind of like end-to-end wireless system design. So this is another model that is called autoencoder or end-to-end learning. So what you will do, you have a like a neural network. One neural network you can use for transmitter, another neural network you can use the receiver. Then you have a wireless channel. So you have a data bits here and you have a received data bits here. So transmitted data and received data, you have a wireless channel between them. So this two neural network you jointly, that is a transmitter and receiver, jointly optimize. Okay, by considering the loss between this received data bits and transmitted data bits. So channel information you can put them. Okay, put on that neural network optimization problem. So this is called autoencoder based approach or end-to-end machine learning based approach. So I'm just giving one example quickly of AI ML in the OTFS system. So we're using the deep learning based approach. So you have a OTFS system. Then what we are doing, this hardware impairments. Okay, hardware impairments are there. For more details, maybe you can refer this paper. So hardware impairment, you can think like IQ imbalance you can have. Okay, like in phase and quadrature phase component mismatch. You can have DC offset, like this kind of hardware impairments we can have. So in phase and outfit or this hardware impairments generally are there in the practical systems. Why they are there? Because currently we are moving to the high frequency band. So like exact designing exact component design at high frequency is challenging as compared to low frequency. So some kind of perturbations are there. Then you can think high mobility scenario that can also can create like imperfection in the hardware because due to the malfunctionality, all these things, or fast switching kind of thing. Okay, so this hardware impairment scenario we have tested AI, the deep learning model. So this is the OTFS system. You can have the delay Doppler domain data. Then this is the like a transmitter. Then I've been doing all these things, CP and then I50, and this is the IQ imbalance. Then you have a DC offset. Then you are transmitting the impaired data. So this is called like a transmitter impairment. Then it's going to delay Doppler domain channel. Then you have a receiver side, that is RF front end. So that is the down converter. Then IQ mismatch also there. So this is called receiver impairments. Then you have a DC offset. Then you remove the CP. Then you have a like SFFT, like symplectic finite Fourier transform. Then you have a data in the delay Doppler domain. So when you have a data here, transmitted data in the delay Doppler domain, you have a received data in the delay Doppler domain. So this data is affected by this hardware impairment, that is a receiver front end and then the transmitter front end. So this is called impairment. So received signal have certain kind of impairment. Okay. Then you can see that when impairments are there, then performance is going to degrade. Performance meaning is that maybe I'm talking about better rate performance, or maybe I'm talking about data rate performance. Okay, and data rate, achievable data rate. So so how we'll do design the like a better decode the data from this YDD, that is in the presence of hardware impairment, so that we are looked through the DL based system. So what we done, we have like data that coming, that is through the output of the channel, that meaning is this data YDD. Then this is we are doing the data augmentation. Okay, then we have a data, both data are added. Okay, so this is the data augmentation part. Then we have like a high dimensional vector nm here. NNM is representing the grid size, because OFDM system is 2-dimensional. So how many horizontal grids you have, how many vertical grids you have, so that way you can understand. And then C is a concatenated data size. So this is a real like imaginary to real converter. So C is a here 2, here is also 2, so that C cap is going to 4. Then you have a some like a neural network that has a certain layers, the hidden layers, then some activation functions, then you have a output layers, then you have a like a classified data here, or that is the output data. So by training this neural network using some generated data, okay, then we tested data in the new data set. Then we highlighted the performance. So impact of hardware impairment, you can see that maybe in the OFDM system, people know that what is the impact of hardware impairment. Generally, hardware impairment create the image frequency. Okay, so image frequency create the interference. That's why system performance is going to degrade. So we have explored like what is the impact of hardware impairment in the daily Doppler grid. So this is, for example, daily Doppler grid, and you have a just single pilot. When you have a hardware impairment, then you will see that you are not transmitting only the single pilot, you are transmitting the 2 pilots. So image copy is created. You can think this is the Doppler, that is the third, and then fifth is the image frequency component is created. So this will create the interference when we have a data at here. So this kind of thing you can think. So extra or image frequency components are appearing in the grid or daily Doppler grid when you have a imperfection or hardware imperfection, that will create the interference in the symbol and in the system, and then it will reduce the performance of the system. Then we have a two-tap channel. So two-tap channel meaning is that it has a delay 0, Doppler 2, and delay 2, and delay Doppler 1 unit. Okay. Then if you see that corresponding to this only single pilot, we can have a multiple copies of that data. So these multiple copies are coming due to this hardware impairments. And so actually we should have only like 4, but we can getting 8 copies. So that is the effect. So this, you can see this desired data and the image data, that is the interference. You can have interference. Then here maybe actual data you have, so we have interference. So a lot of interference will come. Okay, then like we have to have either we have to like perfect hardware, or we have to compensate the effect of hardware before going to the data detection. Okay, so that is a one approach. Suppose data compare like overcome this hardware impairment effect, or we modification in the received data YDD. You have some pre-training kind of thing. You can use some pilots, okay, to overcome this hardware impairment effect, but that can have a further complexity in the system. So what we have done, we have explored this AID or DL based approach. So we haven't done any compensation. We just directly decoding the signal using this YDD through the neural network. So YDD is fed here. Then we have done the decoding using this deep learning model, and then we have an output or data symbols here. Then we highlighted the performance here. Okay, so you can see that this is the maximum likelihood detection performance. That's the message passing that is very close to maximum likelihood. So this is the ideal performance, but you have a hardware impairment. So BR better rate is going to like saturate. So you can see like significant performance degradation is there. But if you can have like a ML model or AI ML in the system, you can have like this pink pink curve is there, so that you can see that around 20 dB you can have like 10 to power minus 2 performance BR. Okay, that is further improved using some channel coding technique like LDP SQL or polar code, and that is good for practical system. Okay, so that way we can say that without doing any compensation, with the help of AI ML, we can have like a better performance. Okay, and the complexity is not going to significantly high. Okay, why we are not going to high? Because model we have trying to learn offline, then trend model we are trying to deploy in the online mode, so that performance like that we can manage the complexity with good performance. So that is from my side. Then I'm just summarizing that my talk. So we have like understand why machine learning or AI ML people techniques people are exploring, and then what the use in the wireless communication. Okay, then we have seen what is the OFDM system, that is a backbone of 4G and 5G communication network. Then what is the drawback in the OFDM system? Why OFDM is not suitable for high-speed communication scenarios? Okay, because the Doppler effect. Doppler effect is a problem in the OFDM system. Then people think a different system that we're calling orthogonal time frequency space modulation (OTFS) system. So that OTFS system by designed by considering the delay spread and Doppler spread both. That is the physical parameter of the channel. So when you consider all the aspects of the channel, then definitely you have a better system. Okay, then we have seen that OTFS system is not too much complex because just extra block at the transmitter and receiver side of existing OFDM system. Then we have highlighted one AI/ML application in the OTFS system through the hardware impairment. Okay. Then we have also highlighting here certain challenge that related to AI, like data quality and availability. We should have certain kind of standardized data set to check the algorithm when you have the AI/ML algorithm for wireless network. So some certain data set, if you can have a standardized data set, we can check that our algorithm. So we can have like certain kind of a standard. Otherwise, like authenticity of the data or that your results, people maybe can question. Okay. Then you have a computational complexity. Still like AI/ML, if you just deploying on the hardware, maybe you have more complexity, you have a like more processor, or like a fast processor. So that way we have to think. Then understanding the AI results, you have to like have some kind of like decision making on the results, so that the interpretability issue is still there. So we have to have some kind of interpretation of the results if you are using the AI in the system. Okay, so that's why people currently saying that the explainable AI or something. Then the regulation and the standards issues, like currently like no regulations of the AI based wireless system design. So we can have certain kind of regulation and standards to like uh, design the AI based wireless systems. So these are the some possible challenge or the limitation people are exploring. Yeah, so that's from my side. If you have any question, I am very happy to take that question. Hello.
Participants, any question? Okay. Okay.
Yeah, sir. Good evening, sir.
Thank you, Dr.
Good evening,
Sandeep.
Yeah,
sir.
good evening. Yeah.
Good evening,
Yes,
sir.
yes.
Yeah, good
Can you
evening.
hear me?
Yeah, yeah.
Yeah. My question is, how do reinforcement learning algorithms optimize hard workers in mobile networks?
Oh,
You
okay,
already
okay.
mentioned in comment box also.
Yeah. So if you think the reinforcement learning, so reinforcement learning, generally people are using the Q learning, one algorithm that can help to implement the reinforcement learning. So Q learning, what we are doing, we have a like a certain states, and each state you're doing certain action. So you have the some reward kind of thing. So like based on the reward, you can doing the action. Okay, if you're giving the positive reward, then you can think like you are doing good. Okay, if you say give some kind of bad reward, then you can doing like not good. So you have to like change your action. Okay, certain kind of thing. So Q learning algorithm people are exploring. Maybe some other algorithms are there. So my student have implemented Q learning for beamforming optimization that we currently submitted somewhere that paper. Okay, but if you just asking me the Python code, that I don't know exactly, but the idea, what the idea for beamforming or like a Q learning, that I have, just that is the idea. So that is the cumulative reward. Basically, you are optimizing, or cumulative reward you are learning, looking when you designing the reinforcement learning in the wireless network.
Yeah, sir. I got your point. I understood.
Yeah.
And I have another question. What is the significations of AI or ML? I
So
mean,
any
machine
other
learning in
question?
self-organization. Sir, can I hear me?
So thank you everyone. Actually, maybe I haven't gone like too much details, but I have given the idea like what you have thinking in your mind when you thinking like AI, applying the AI ML in the wireless network design. So I've given some idea in the WebDM system or OTFS system. So I also explored like new dimension, those who are looking like what is the new technology or what is the new waveform people are exploring for the next generation wireless networks. So you can explore the OTFS technology. That is another technology. Okay, that may be better as compared to WebDM. Okay. Uh,
Okay, Sanjeev
Sir,
sir.
hello. Sir,
Thank you for
sir,
taking the
can you
time
hear me?
yeah. Anything else?
to share your
My
expertise
voice
with
is
us.
audible?
Yes. Yes, Nagaraju, you are audible.
Hello.
My voice is audible, sir?
I think yes, you are audible. Please ask.
Hello.
So I think if no
Yeah,
questions, then we
I have
can
a
stop.
last question. Yeah, I have a last question,
Dr.
sir.
Arvind.
I have a last question. Sir,
Sanjeev
can
sir,
I hear me?
Cannot hear.
one more question from the
Only questions are
participant.
there, sir. From my side.
Yeah. What is there any question?
No, sir,
Actually,
I
sorry. I think.
already mentioned in comment box also. What is
Oh,
the significations of AI and ML in self-organizing networks? I mean SON for the next generation wireless systems.
self-organizing the network for next generation wireless network. I think self-organizing meaning is that you can think that maybe I can give one example. In the hardware impairment scenario, for example, if you can thinking that is a like hardware point of view. So when you have a transmitted data, that data is going through the like hardware impairment, then you have a certain voicing or like a rotation or a scaling in the data. Okay. So this kind of experience is happening in the data, then maybe you have some AI ML techniques, okay, that will modify your input data itself, okay, so that when this modified data will go through this impairments, then you can have like a normal kind of data, okay. So like you can have certain kind of tuning those data points, okay, with the help of AI ML. Even if you have a hardware impairment, you will really or like actually not have that impairment, because that impairment taken care by this AI ML algorithm before going to that hardware. Like that way you can think. So self-organizing, that is a like self. So that way people are exploring also AI ML, because you can manipulate the data after modulation. You manipulate the data, because AI ML knows like how much hardware impairment is there. So what is the amplitude imbalance? What is the phase imbalance? So that can pre-compensate it, like that way you can think. So that way you can think something is like some disturbance in the network, and but if AI ML like algorithm or can predict those like a disturbance or the normality in the network, that then they can take care of itself. Like that way you can understand.
Yeah, thank you, sir. Thank
Yeah.
you. It's nice. Thank you.
Yeah. Thanks.
Okay, I think Dr. Sanjeev, all the participants are satisfied. So I greatly appreciated the knowledge and perspective you shared. Thank you once again for the taking time you shared your expertise with us. Your lecture was truly enriching, and I think all the participants will forward your knowledge and insight the gain. Okay.
Yeah, thanks.
So thank you
Thanks,
once
Dr.
again, Dr.
Arvind
Sanjeev.
Zay. Yeah, thanks, and thanks
Okay.
for every participant. And if you have any query, especially regarding this OFDM, OTFS, okay, and how we'll apply AML in the OFDM or OTFS system, please let me know. You just write me the email. Maybe I will share code. Okay, I will share that all the details if you need. Okay, or we can discuss sometimes like you just send me your query, then we can have some kind of meeting and we do that. Okay.
Okay, sir. Okay, thank
Yeah.
you. Have a good
Yeah.
night. Okay.
Thank you. Good night. I'm sharing my email, so if you need, you can do it.
Yes.
Yeah, that will be good. Uh, because just listening, I think we cannot understand, but once we do something, then I think we can learn something.
Yes.
Yeah, so I have shared my email ID. So if you have any query regarding OFDM OTFS, like or how we employ the DL in the OFDM or OTFS system, like classification or the beamforming, like that, so we can discuss.
Okay. Thank you.
Yeah.
Thank you,
Yeah.
sir.
Thanks, everyone. Yeah. Thanks.
Okay. Bye bye.
Bye bye.